State Electronics, Department of Electrical Engineering, Uppsala University, Sweden. I also welcome all the faculties and the students for joining us on this auspicious day. Now I call upon Apeksha Ziraj to introduce our first speaker, Dr. Sriram T. Rajendran, postdoctoral researcher, Bioinnovation Institute, Denmark.
Thank you, Varshini. The first speaker for today is Sriram T. Rajendran. Sriram T. Rajendran has completed his BTech in Biotechnology from Anna University, Chennai, and MSc in Biomedical Methods and Technology from the Department of Biomedical Sciences, Malmö University, Sweden. Later, he joined the Center for Intelligent Drug Delivery and Sensing using microcontainers and nanomechanics as a PhD student under the supervision of Professor Anja Boysen in the Department of BTO Nanotech, Technical University of Denmark. Sriram has also been a visiting researcher in the Department of Mechanical Engineering, Dublin City University, Ireland, and at Biomems and Bioelectronics Laboratory, Louisiana State University, USA. Later, Sriram joined the team of Professor Anja Boysen at Bioinnovation Institute, Denmark, as postdoctoral researcher since June 2020 for developing sensing platform for therapeutic drug monitoring. Over to you, sir, and thank you for accepting our invitation.
Thank you very much. Can you guys actually see me?
No, sir.
Okay. There's okay. Let me start sharing the screen once again. Just bear with me, guys. I'm having some issues launching the presentation. Yeah. Okay. It looks like still I cannot, for some reason, share this. Let me do something. I will just relaunch my application back. I will exit the meeting and get back online again. Yeah.
Sure, sir.
Okay, so I'm back online, but I have, I don't know, for some reason, I'm not able to have my video cam on. Okay, that's fine.
Share the presentation.
Yeah. Okay, there we go. So can you guys see my presentation?
No, sir.
Not yet. Okay. Okay, I have no idea why this is happening.
It is loading, sir.
So just give me a confirmation once you can see my screen, then I can start going. You guys can still not see my presentation yet?
No, sir, still not visible.
Is it okay if I actually, if we can move to another alternate platform just for the sake of time?
Good morning, Vikram, sir.
Morning, sir.
Sir, now we are going to start the first
Yes,
session.
sir. Yes, sir. I am seeing, sir.
Yeah.
Sir, I hope there was a problem with the speaker's presentation issues, sir. I will wait, sir. No problem.
All right, I have shared my presentation once again. Maybe it's better I send the presentation. Okay, it's I can see it's loading up. Perfect. All right, let's go then. I think it's better I present it in this format. It's hard to really control. Okay. All right, let's start the presentation. Good morning, everyone. I'm really sorry for the technical problem here. It's not a platform that I usually use. Oh, okay. Can you guys hear me? I'm not sure whether I'm audible to you guys.
Sir, you are audible, sir.
Okay, perfect. Okay, let's keep going. Yeah. So good morning, everyone. My talk today is titled Custom Instrumentation for Biomedical Applications. So this is a talk more focused on, it's one of the developmental journey of an instrument that we developed in our group. And more specifically, also, I wanted to sort of inspire you guys to think about why custom instrumentation is important and in which angle to think. So to give you a very basic perspective of the need for different types of custom instrumentation for applications. And more specifically, I think I will also give a brief introduction about sensors, more specifically into electrochemical sensors. And then later into microfluidics, then a little bit of point of care diagnostics and the concept of micrototal analysis that's called microtas. And then I will show you also a little bit about our device development and some other relevant information. So to go further, I don't know how the previous presentations were, but I could very much like to have this presentation a little bit more interactive. So you can always feel free to interrupt me if you have any questions, so we can take it in a slow pace. So I think that will be rather easier for the information flow. So it's better to ask the questions as we go. So either you can sort of write it in the chat, or maybe you can raise your hands and I can take up the question. And there might be some sort of questions in between. So please feel free to answer from the audience. Yeah. So I'm a postdoctoral researcher at Technical University of Denmark, and also partly at Bioinnovation Institute. So that's a place of work. It was until 2 weeks ago. So now my affiliations have changed, but these are my old affiliations. Just you know. Okay. So going ahead, if you see this graph, this is the life expectancy of humans globally. From the year 1770, since we started making the record, until 2015. And you can see that the life expectancy has suddenly increased after a particular time instant here. And this is very interesting aspect, because this is where a lot of world wars and stuff happened, but then suddenly there is an explosive growth of population. So does it strike you guys why did it happen around this time? Anyone?
Development of medical.
Yeah, exactly. That's right. That's absolutely right. So in this time period, so after the World War, more specifically, there were so many technologies that people have invented for war purposes, and then after the war, they had to sort of repurpose some of these technologies to something more beneficial to the society, and then suddenly there is an explosive growth of medical devices, some very large medical devices. Like you see in terms of X-ray, HPLC, mass spectroscopy, NMR, and many such instrumentation. So what has happened is our capability for diagnostics has increased tremendously after the World War. So typically what happens is there is a patient or somebody needs to be tested. The person goes to a hospital or a centralized lab, and they get the diagnostics done. So it's more, or sometimes you might have to collect samples. So the patient goes from the home or wherever they live, and then they go to the hospital or centralized facility like diagnostic center for giving their samples, like blood sample, urine sample. And then finally the result is declared, and probably you get a result via email, or maybe your doctor calls you and tells you the information. And that can happen anywhere, most likely in the patient location. So, so these are all involving a lot of logistics. A person has to move from one place to another place, and there is a lot of time lag in which the analysis has to be carried out, and the results are coming out, and then a follow-up reaction. Just let me know if I'm too fast. Please let me know. I can slow it down. Yeah. So this is where we get interesting. So what if we can bring all these things together: sample collection, sample handling, and result all in one go, and that happens very quickly. And that is exactly what you're talking about, point of care diagnostics. So it is it's conceptually a device where the sample collection, the sample processing, and the result output comes exactly on the same device, a little device. And very conveniently, that can be done at the patient location. So can you imagine a simple point of care diagnostic device from this example I mentioned earlier in the slide? Any ideas? There are so many point of care diagnostic devices available. I'm sure you might come up with some idea. Just give a wild try. You can write it in chat, or maybe tell me what you feel about it.
That medical wristwatch.
Yeah. So those are called medical wristwatch. You mean like a smart wearables, like the smartwatch, like Apple Watch? You mean?
Yeah. Where we can get BP and other things.
Yeah. So yes, it is also one of the it's really very advanced device actually. It's a 21st century device where you have complex electronics, and stuff involved. So there are more simpler point of care diagnostic devices. Super simple. So your wristwatch needs power.
Thermometers, sir.
Sorry?
Thermometers.
Thermometer. Sure. Yeah. Thermometer. Yes, thermometer is a biomedical device or a sensor. It's more. I think it's more a sensor, right? So you measure a particular parameter. You don't sample out any biomedical samples like blood or something. Something very simple, super simple. That has been popular for last, I don't know, 20, 30 years or something. So yes, let me tell you a good example. One is the pregnancy kit. It is super simple device. What you do is put some drops of urine in one end of the device. Probably, I think it's in this case it should be this side of the device here. And then what happens is there is a paper. So it's basically it's a lateral flow assay. The urine sample actually flows through the paper, and then there are some chemicals that reacts, and then you get a mark. So if you have a single mark, then one is not pregnant, and if you have 2 marks, then well, the sample says that the person is pregnant. It's a very, very simple device. It needs no power. You just add a few drops of urine, and then you get the result. So to give, okay, it's a lot of information here. Let me guide you one by one. So if you see the pregnancy test in 1950s, people were doing very silly tests. Actually, what they do is if somebody has to be tested if they are pregnant or not, what they do is they take female urine sample and actually inject it into a frog. So female urine samples have a hormone called human chorionic gonadotrophin, HCG, in urine, usually found in pregnant women. And if that is the case, that causes ovulation in the eggs, in the frogs, and then the frogs will actually lay eggs. Well, if the frogs lay eggs, then you can say that the sample is positive for pregnancy. And if there is no hormone and then there is no eggs, then you can say it's negative. And that's how the samples were done. Can you imagine how the diagnostic lab could have been full of frogs, a lot of urine samples, people growing frogs to get the result here. So that's how ridiculous it was in 1950s. But then now sorry?
It was in the year 1950s.
It was in 1950s and 1960s. That's how the test was done. Yeah. It's even later. I think even until 1980s in many countries, people are doing this kind of test, if I'm not wrong. Yeah. So, well, thanks to the technology, we have, the current age in 2021, you can go to a nearby pharmacy and buy these strips, which is not very expensive. It's super cheap. It's the same concept. The pregnant women have a HCG hormone in the urine. And if you put the urine, few drops in the device, you get the result in less than 10 minutes. And the funny fact is its accuracy is more than 99% actually. It's pretty accurate, really fast, no electronics involved, super simple. And then the best part is it all can be done anywhere, wherever the person likes, in the home, in the office. So this is exactly what you call point of care diagnostics. So let's increase the complexity a little bit. So if you want to, can you imagine any other point of care device that is so popular that you can go and buy from a pharmaceutical, from a pharmacy nearby? Any other device? There are many popular devices like that.
Sugar testing, sir?
Yeah, exactly. Absolutely. Yeah. Yes. Glucose testing is one of the highly sold diagnostics device ever in terms of for commercial use. So that's called glucose meter, and it's pretty common. There are a lot of fancy versions now. So you basically take a drop of blood. In a way, here you don't have a lateral flow, but you have a more like a capillary flow. The blood, once you put the drop of blood, it goes into the instrument, into the test chip, and then what you can see is a readout. It tells you exactly what is the glucose concentration available. But then the mechanism, if you see, it's not very complicated. There is a sensor surface, and then there is also some enzymes on top, which is typically a glucose oxidase enzyme. So when there is glucose and oxygen along, there will be hydrogen peroxide produced. And that hydrogen peroxide actually shuttles electrons towards the electrode. That is what you measure as current. So the more current you get, the higher the blood glucose concentration is. However, I just have to really say that this accuracy for this glucose meter is not really high, actually. It's between 50 to 70%. So there are pros and cons, but here the focus is for a glucose meter, you don't have to be accurate. What you are interested in is to know the modulating levels of glucose in your body. Yeah, so that's the most important aspect of the device. So you have different use case scenario, and you have different level of accuracy required. So you don't have to be always accurate in point of care diagnostics. So in this case, 50 to 70% accuracy, it's fine. What you want to see is just a change in the level, which is okay. So if you compare both the devices, pregnancy kit and glucometers, I can call the pregnancy kit as passive device because it needs no power. Glucose meter is an active device. It needs power. It's a battery powered device. And of course, since there is no electronics involved, super simple construction, pregnancy kit is much cheaper. And then the glucose meter is it's relatively expensive. And then the most important aspect is this device, the pregnancy kit is a qualitative test, meaning it will give you an answer yes or no. You cannot quantify how pregnant you are. It's just you're pregnant or not. But in terms of glucose meter, you can definitely quantify. You can get a specific number that is more quantitative analysis of the biomedical parameter. So that's a higher degree of complexity. So now taking this understanding even further. So let's say we have even more complicated fluidics. So here the blood is just flowing in a capillary flow. So let's say you add the sample, you do more complex analysis of your blood or urine sample, then you analyze, and then you have a sample readout, all in one go. And then this concept is called MicroTAS, Micro Total Analysis System, or it can also be briefed as the symbol micro and TAS. So MicroTAS is a really popular concept in terms of fluidics. Since 1990s, there has been explosive amount of research work coming out in this domain, primarily due to our improved manufacturing capability in terms of nanotechnology. With more clean room techniques available now, we can make more and more smaller devices. So that's how you are able to get more complex electronics, CCD cameras and stuff. So if I have to dissect MicroTAS, MicroTAS has two components. So one is the sensing component, the other is microfluidic component. So let's take this one at a time. So if you see the evolution of analytical platforms, in the earlier slides, we have seen what has happened in 1950s with a lot of diagnostic equipments coming up. But those are all huge equipments. X-ray machine is huge. NMR and mass spec are huge machines. But on the go, since our electronics capability have improved quite a lot in terms of clean room fabrication and nanotechnology, we can make the device smaller and smaller and also more complicated, more complex in terms of architecture. So compared to the 1950s, in earlier 2000s, and even now, we have even more and more powerful devices, but they are getting smaller actually. So this is a very interesting trend. And so the advantage being the blood analysis, for example. It's like a tabletop device. It's a little bit larger than your microwave oven in your kitchen. It is so small that you can actually fit it. Many of the ambulances actually have such devices. So by the time the patient is being taken from the home towards the hospital, the emergency response team can actually run a basic blood analysis parameter. So there are CRP levels, blood glucose level, blood oxygen level. So there are at least like 15 to 20 parameters that is very essential for an emergency room doctor to give an appropriate response in an emergency situation. So every minute matters in terms of emergency. So the patient doesn't have to come and wait until we get the results in the emergency room. So these tests can be carried out as the ambulance is going towards the hospital. So that's a significant improvement in our quality of life. So once you go to the hospital, the results are already ready. It just gets printed, all those 15, 20 parameters. The machine can print like a bill. When you go to a shopping mall, after the checkout, you get a little slip, right, with all your billing materials. Exactly the same way, there is a little printer in the machine. The machine can print all the parameters. And then the emergency room doctors can respond appropriately, really fast. So the other example of analytical platforms are, I don't know how many people have, how often people travel these days, but in general, if you see the airports, many airports have detectors for drugs. So they do a random check, they do some swipe and check. It's a quick analysis if you are somehow carrying a drug substance or explosive substance in a bag. It can detect even minutest of concentrations in terms of nanograms. So that is what you do at the security check in the airport. It is really another small machine. It's slightly larger than a microwave. Maybe it's a little bit bigger than, it's larger than a microwave, smaller than a washing machine, you can say. That's the size of the device, to give you an idea. And more recently, I think somebody was earlier telling me that there is the Smartwatch concept. So people have also evolved. So Smartwatch is something very interesting because you get the parameters continuously. It's not like you measure your parameter every 2 hours or every 3 hours. You can get your parameters recorded every minute.
Sir.
Hello? Yeah, sorry. Yeah, sorry, I had a little bit of a disconnection here. Yes, so the recent trend has been more continuous monitoring. So having this parameter recorded almost every minute, which is great actually, because you exactly know what's happening in real time, which is very important. So to give you an illustration of why this is important is I have a little bit of an example here. So let's say you're measuring blood glucose level, and then in the x-axis you have the time. And let's consider each of these lines is 1 hour, first hour, second hour, third hour, fourth hour, and fifth hour. If you are doing a usual test with your glucose meter, what you do is every 1 hour you just prick your fingers, take the blood sample, and you get the concentration. You do it every 1 hour. But what could have happened is the blood concentration could have fluctuated like this. So you don't know what's happening in between these 1 hour time range. And sometimes that information is essential for certain patients. So then in that case, real-time sensing or continuous monitoring is very essential. So glucose meters have become so advanced now that you can actually have a little bit of a like a coin-like device with NFC tag in it, with a little micro needle. So the needle is embedded under your skin, so it can sort of have access to the blood continuously. So if you need to just measure what's happened, what this device does is that it actually records blood glucose concentration in a time that you program through an app in the mobile phone. So if you want to see the output, you just take your phone and tap it on top because it's just NFC. So just go nearby, and then the data from this device is transferred to your phone, and you get this in real time. This device is right now available in pharmacy, and actually, many people in India also use this. So it's not that difficult to make such devices anymore. So why custom electronics? Still, there is a lot of need in terms of how we do some analysis. For instance, it has been really popular to actually have a small device that can be connected to your mobile phone, for example, and have a small analysis unit and then power it, because some analysis unit definitely needs some power. For example, there is a brand called FLIR, which sells IR camera. The IR camera module is as small as this, and you just connect to the USB port, USB-C or mini USB port under your phone, which will transfer the power from your phone and does the analysis. So the need for analysis has been always increasing. Also, even during the Corona times now, you can see there is an improved need for diagnostics. Imagine if you had a device like this, which can measure a given sample. You take a throat swab, take a sample, and measure in 5 minutes. How useful it is for us. It really changes the quality of life significantly. So that's why we need custom instrumentation sometime to start with the research and development activities in the lab, to see it as a prototype, because many of these large instruments are very expensive. You cannot tweak them. You might be interested in adjusting certain parameters, but because of the cost factor involved, and many of the manufactured instruments do not have the flexibility to do changes. So in that case, we definitely need more and more instrumentation. So having seen how the diagnostic industry and also the miniaturization of the device happen, I could like to give a very brief introduction to what electrochemical sensors are, and more into electrochemical measurements. So you guys are all from engineering background, so you know the concept of sensors. So you usually have an input signal to a receptor plus transducer, and then you get a certain output signal, which is measured and given as a value. In general, you can see three major classes of sensors. One is optical, one is electrochemical, the other one is mechanical. So the smartwatch example, which was told earlier, is a very good example of optical sensor involved. So you can see like sort of a green LED or a red LED sometimes in some cases to measure the blood oxygen level. And then the other good example is electrochemical sensor, which we also discussed for glucose monitoring. Then there is the third class of sensor, more into mechanical, like nanomechanical sensors, cantilever-based sensors. Well, those are not really practical in terms of for mass market application. So that's why exactly optical and electrochemical sensors are more prevalent. It's more common from a product point of view. So basically, what an electrochemical sensor does is you have an analyte that is getting you have a chemical reaction going on, either oxidation or reduction. Whatever it is, you will have a transfer of electrons. And then that electrons goes towards or away from sensing surfaces. Either the electrons goes in or out, can be a positive or a negative current, and then you get a current output. So if the analyte you're measuring, if it can directly oxidize or reduce, then it is called electroactive analyte. That's the term here. And then there are some analytes which do not directly do this. You need an intermediate step for this electron transfer to occur. And in that case, rightly, it's called non-electroactive because it needs more processing. So a good example, again, once again, is blood glucose measurement, because the glucose itself cannot oxidize on top of the sensing surface. What happens is there is an intermediate step where you need an enzyme to actually do this process and thereby transfer the electrons, and then you measure. So since I've already introduced glucose measurement, so this is perhaps easy for you to understand. And this is exactly the concept of a biosensor. You need a biorecognition element for capturing the signal and then shuttle the electrons, and then you measure. So how does an electrochemical workstation looks like? It's not that fancy. That's how it is. You just have a small device. This is almost the size of a computer CPU. You have a control terminal, and then you have the program to control this machine, and then you just have like 3 wires coming out of a few wires, and that's the electrochemical cell. So it's nothing fancy here. And this machine is it's called Potentiostat because it can control potential, and also it can actually control. It can either be a potentiostat or a galvanostat, meaning the galvanostat can keep the potential constant and measure the change in current, or the potentiostat keeps the potential constant and measure the current. And then the device can also vary depending on the requirement and the type of measurement, we can do more such modifications. To give a very brief introduction about an electrochemical cell. So I will give a classic example of, on the left side, you can see that it's a 3 electrode system. So this is like a little beaker where you have 3 electrodes immersed in a solution. So what happens is you have 3 electrodes. One is called working electrode, one is called reference electrode, the other one is called counter electrode. So what happens is you apply potential between the reference electrode and the working electrode. That's why it's called reference electrode, where you have one electrode which is thermodynamically stable. So if you apply a potential with respect to that potential will remain the same. And the reaction is happening on the working electrode, as the name indicates. And then what happens is the reaction is happening on the tip of the working electrode, and then the current is flowing through the counter electrode. So you apply potential across reference and working, but then you measure the current between working and the counter. So that's the concept. And yeah, for the electronics people, I think this is a circuit for you to understand. I think I'm not really into electronics, but maybe this circuit diagram is perhaps makes you understanding better. It's exactly this is equivalent to this electrochemical cell. So you have a reference electrode here, you have a working electrode, and this is the counter electrode. So it's sort of a feedback loop where you have an op amp with a feedback loop. So it's a very simple construction for a potentiostat. That's the basics of potentiostat. So also in terms of potentiostat, we can see that it can be used for several applications. For example, potentiostat electrochemistry as a concept is used for developing batteries for corrosion and electroplating. It's very popular technique, especially batteries, especially these days. There is so much battery application in terms of lithium batteries, lead batteries development. Then a lot of biomedical applications can also be done in terms of measuring analytes, then point of care diagnostics like glucose meter once again. So all this, while all this development is happening, so I mean, typically the electrochemical workstation was used for large applications like battery and corrosion, and then it only came to biomedical application after the invention of Clark electrode in around 1953, 1960s, in that time period. The explosive growth as point of care diagnostics came after 1986. That's where the first glucose meter was developed in Roche Diagnostics it's a group in the US. So the size of potentiostat has also significantly it keeps going smaller and smaller because, again, advancement in electronics. So in general, what happens is to give you a little bit insight into what I mean by size of potentiostat, I will give you a specific example. So this first picture, this is a very old analog potentiostat, meaning that you have like knobs and buttons, like pretty old school style. It's not digital electronics, purely analog. The output of this instrument is actually in a chart strip reader. I don't know how many people have seen a chart strip reader. It's more like a seismograph for the earthquake. You get the sort of a wave whenever there is an earthquake. So basically, this machine gives an output in a chart strip reader because there is no digital electronics involved. And then, of course, it is computationally very limited. It does only one job. For example, this machine particularly does a technique called amperometry, meaning it can apply a specific potential, and then as a result of it, it measures the output current over the period of time. That's it. You cannot do any other changes. So it's highly limited, and it's a really bulky instrument because it's analog. And then with more modern technologies coming in late 1980s, late 90s, you have the computers have started developed. You have some color monitors and more complex CPUs. So then suddenly you can do some more complex programming in terms of how you control the potential, and then you can do some fancy measurements. So this is an example of an electrochemical cell, how it looks like. To give you the idea of the size, next to this is a 250 ml beaker. So just to give you the size perspective. So this machine is this potentiostat is in the weight range of 4 to 5 kilograms. while the latest generation of potentiostat is super small. It's as small as your hard drive, the portable hard drive that many people have. And the sensors and what has also happened is this electrochemical cell is also now miniaturized like this. So this particular thing is called screen printed electrode. It is about the length of like 3.5 centimeter, as you see from the scale bar here. So the instrumentation is also becoming small, and the experimental platform is also becoming small. So that's a brief into electrochemical measurements so far, and now we will go into the other part of the microtest. So microtest, we saw earlier that it was sensors and microfluidics. We finished the sensor part, now we are going to the microfluidics part. So the concept of microfluidics, I don't know if you have been introduced before, but it's very simple. As the name suggests, micro, it's small volume. It's really small volume. It's very cost-effective solution because you use very small volumes. If you want to do some complex analysis, there are some reagents that are very, very expensive. You don't want to waste them. You don't want to use a lot of volume of those expensive reagents. The less you use, the better it is. And then since the device is small, the diffusion is faster, meaning the analysis speed of how fast the analyte mixes with other reagents. So that's a general, it's a very, very short, microfluidics is a huge field. I'm giving a super simple introduction to microfluidics in one slide here. So how does the experimental platform look like? So this is, for example, a microfluidic chip. You see two inlets, liquid is coming in, and here the mixing is happening, and then the liquid is flowing, and this is the outlet. To push the liquid, you need some instrument, right? So then you use sort of a syringe. So in general, you can just use a normal syringe to push this. But since the channels are so narrow, you need a lot of pressure to push the liquid. So then you use an instrument called syringe pump. And it's a very simple instrument again. You just mount the syringe, and then there is a there are threads, and the machine will just keep pushing it, so the liquid comes out. It can be done in a very precise and controlled way, and that's how the chip looks like. People, if you want to see, if you want to monitor the analysis, what's happening in between, you can straight away take this under a microscope and see what it is. So this is it's a cartoon representation. So syringe pumps have also become more smarter. So it can look like this, and then a small tubing, maybe put a liquid in a test tube or something, and then push the liquid from there to a microfluidic chip. But microfluidics has its own problems. It's complicated because this is one of the very simple setups actually. You have like 2 inlets and 2 outlets. Sometimes it can be like 16 to 20 inlets, 16 to 20 outlets, and then there will be suddenly so many tubings, you don't know which tube is going where. And of course, there is a lot of problem of leakage because you're using a lot of pressure here. And you have to figure out if you're using 16, 20 tubings, you need to know which tube is exactly leaking. It's definitely a nightmare sometimes in the lab. It takes several hours for you to even understand what is going wrong. So here, this is where people can think about what are the other ways that we could pump the liquid. So can we not find any other better way to pump the liquid through the microfluidics? Why should we do it the hard way? So then one could potentially think of centrifugal force. For example, if you go to a sort of a fun ride in a theme park, you do this ride. When it is rested, you sit like this. But when it rotates, you really move outwards, meaning you have centrifugal force. Can we do this? Can we do this for fluidics? Is a question that some researchers had a few decades ago in early 2000s. And then they actually came up with an idea. So and that is exactly is called centrifugal microfluidics. In this case, what you do is instead of pushing with the pump, you actually load the liquid in the center of the disc, and as it spins, the liquid comes out. So the centrifugal microfluidics does exactly what the typical microfluidic does. That is metering. So metering means you can actually measure how much volume is going out. You can valving means closing and opening of the liquid flow. Whenever you want to stop the liquid flow, you can stop. Whenever you want to go, you want to pump the liquid, you can do it. You can do the same in the microfluidics.
And then in microfluidics, one of the important aspect is mixing. Your analyte should, your biomedical analyte should mix with other reagents for the reaction to occur. If the mixing is poor, then you don't have a proper reaction. Yeah. That is extremely important, and sometimes you need to do filtering also. Sometimes some samples are complicated. It's better to have some sort of filters to take away disturbing analytes. So, do you think it is feasible? Whenever people are introduce centrifugal microfluidics, they all say it looks fancy and stuff, but can you actually make products out of it? Well, that's a very good question. There are centrifugal microfluidics also has its own challenges, but then there are many commercial companies available now that actually sells. These are in the size of a DVD, actually, like a CD, about 100 mm in diameter. So that's 10 centimeter. It's so small, exactly the size of a DVD disc. You just take the sample in one corner. So this is like a pizza slice. So you don't even need to have this whole disk here. You just have one slice, fit it like a cartridge, and then rotate it, and then all the analysis happens within the disk, and then you have a sample readout. In fact, this is one of the device from a company called Blue Sense Diagnostics, headquartered here in Copenhagen, Denmark. It's actually a spin-out from our lab. They are going quite global and big in terms of detection of dengue virus, Zika virus, and also they even developed a fast antibody test for coronavirus. So centrifugal microfluidics is increasingly getting popular. Even Samsung Diagnostics has actually a device in centrifugal microfluidic platform, also Roche Diagnostics. These are big names in diagnostics. So coming to the focus of the talk, so I have given you a fair introduction of what a point of care diagnostics is, sensors or microfluidics are. So now I think you are in a better position to understand what we do here in our group in terms of centrifugal microfluidics. So our group is more specialized, and me specifically, I'm specialized in integrating sensors on a centrifugal microfluidic platform. So we have a centrifugal platform. This is one of the miniaturized sensors you have seen in the earlier slides. So we specialize in combining them in one platform in a form factor of a disk. So, for example, this is a very simple disk schematic we have for one of our papers. So this is the loading chamber. This is where you load the liquid. And then the liquid, once you start spinning the disk here, the liquid is slowly pumped out like this. And then this is called metering chamber. So what happens is the liquid first fills from the bottom to up. And this is exactly 80 microliters. Beyond 80, it overflows here. So this is exactly, it's called metering chamber. Every time it exactly measures 80 microliters and remaining will come out. So the electrodes are embedded under this, the electrochemical sensors. So we can measure as the disk is spinning. So that is the focus of this platform, to have an integrated electrochemical sensors on the disk. Well, the integration aspects are completely out of scope of this talk, but it's more in the paper. I can share you the link later. Yeah. So I want to more give you an idea of what are the challenges actually in detection in centrifugal microfluidics. Earlier you have seen that. So for this for microfluidics, you did a particular experiment. You took this chip right away, straight under a microscope, and you measured it. But what if your system is spinning? Yeah, so we have this problem. Disk is spinning. You should not forget it. And how do you measure it while it is spinning? So then you have 3 different modes of measuring while this experiment is happening. Either a type of method is called off disk, where you actually stop the disk, take from your platform out, and put it into an instrument like a cassette, and then measure it. But then this is not a good idea because you're disturbing a lot of analytes. You don't want to do its extra manual step. The whole idea of doing is to automate this process. So we don't do this. Then the second option is stop spin. So that is, you just stop spinning the disk, but then you can have a like a detector aligned on top and then measure. So you don't disturb the disk, but you can still measure. But again, what you can do is you can only do an endpoint measurement, meaning that after the reaction has completed, only then you can do this measurement. You can't do the measurement as the reaction is happening. So that is exactly is called real-time measurement. Like I've also told you earlier in terms of how this is real-time measurement. So to do measurement during spin is the most challenging aspect of all the three measurements. And more specifically, electrochemistry in centrifugal microfluidics is more complicated because this instrument has to be physically connected to the electrodes. You need to, because we are measuring current. Yeah, so you need to, these are contact points on the electrode. So we need to physically connect the electrodes to our instrument, which is here. And this disk is spinning. So how do you imagine doing this? How can we solve this problem? Well, people have tried the stop spin option for electrochemical measurement. So this is a really nice paper from a group in Dublin. One of the collaborators I've worked with, they actually have an electrochemical sensor here. They do all the analysis. After the analysis, they actually stop the disk. They connect this with the crocodile connectors and then measure with the instrument. As simple as that. But then we want to do something complicated. So we want to measure as the disk is spinning. So then there are devices called slip ring, which are rotating connectors. So you put them on top of the disk platform like this, and then you can. So this is the connectors going towards the potentiostat, and then the disk is spinning. So that's how it looks like in terms of the wire. So it is. You can see this is one type of slip ring, and then this is another type of slip ring connected to the disk. So basically, this disk has 8 detection unit, and each detection unit has a reference, counter, and a working electrode. 3 electrodes. So 3 into 8, 24. There are 24 contact points on this electrode, on this disk, and then you have 24 contact points of connectors to the machine. So you need to connect 48 connections. And that is crazy. So it is really, really messy. Yeah, it's a mess like this, baby. It's horrible. It takes like 4 hours to assemble the system. So this, for example, this system, it took us 4 hours to assemble, purely because we need to ensure that each connection is exactly connected to where it is. Yeah. So we don't want to be in this situation. So what are the alternate ways? How do we connect the centrifugal microfluidic disk with electrodes with the potentiostat? One is, one crazy idea is to put this potentiostat straight on top of the disk and spin it. But that is like 4 to 5 kilograms, not a good idea. Then what if, I've also told in earlier slides that the potentiostat sizes keep decreasing. So why not put a less heavy potentiostat on the disk and start spinning? Sure, that sounds possible. But then you still need, you still have the wire problem. How do you power this device? You need to connect to a power source. Let's say even if you make this a battery powered device, you still need to connect them to the electrodes, which is a physical connection. So the core problem lies in eliminating the wires. Wires is the biggest villain here in the connection. So this is where we decided, okay, let's do something interesting. So what we need, these are our requirements. We need something small and lightweight potentiostat. We need wireless power supply. We don't need any wires. And most importantly, we need to have very stable connection to the electrodes on top of the disk while it is spinning. And obviously the data transfer, after the measurement is done, that data should be transferred to a place where we can process it later. Yeah. Well then, yes, that's what we do. We looked around to shop for such a device. It did not exist. So then, yes, then we started developing our own device. That's going into the custom electronics now. So what are the development aspects? So if you see a custom electronics, you have to think about 4 major aspects. One is, of course, the hardware. How complex you want the hardware to be, and what is the form factor, how big it should be, what is the aspect ratio, and then the software. How do you plan to control your hardware, the software aspect, and also for the troubleshooting. If you should go for a very simple platform where your troubleshooting should be easier. and about data handling. What to do after you get your software. So can you process the raw data is processed easily, or needs another complex software to process the data? That is something you should really think about before you start. And then the methods. Several instruments have several measurement ability. So you have to select you don't have to always develop all the aspects of a machine. You just need to develop the aspect that you are interested in, because you are building a new instrument. So that makes your life easy and your development cycle faster. So then finally we came up with this device. It's called, as rightly named, it's called Potentiostat on a disk. So basically we put the whole Potentiostat like a sandwich with our centrifugal platform. So this is the microfluidic part, a microfluidic disk. So that is sandwiched between two PCBs. One is we have a bottom PCB. We call it a platform with disk holder. That's where we have Arduino controllers and stuff. Then we have the shield where we have electrode connections to the electrode. You can see this spring-loaded gold pins. This sit right on top of the electrode and they spin along. So it's beautifully integrated, that it's connected so well that we won't get much of noise. So that's how the device looks like. So sort of shield placed on top of the electrode, and then we have a LabVIEW program to control the device. The LabVIEW program has been done very elegantly by one of our students in the lab. So what does our device do? Yeah, so our device is basically a potentiostat with the ability to rotate with the disk, but then we don't have wires. We eliminated the wires, and then that's how the final product looks like. It's so small, very elegant, works all the time. Actually, do you remember in the previous slides I was telling, like, why not put the whole potentiostat on top of the disk and spin along with it? Actually, a group tried to do it in US. So it is I think, sorry, I'm skipping too fast. Yeah. So it is this group. It's a very famous group in US, Mark Meadows group, where they have a spindle motor. Then they this is the microfluidic disk, and what they did was they actually made a 3D printed holder, and they put a very small potentiostat. This potentiostat, by our development journey, took almost 3 years for us to develop this instrument. So in meantime, what happened was that technology and the world is moving so fast that the potentiostats became even smaller. So they just put an even smaller potentiostat on a 3D printed holder and started to spin along with it and measure. And that was published in 2019, just a few months before we submitted our paper. So basically, this is a one-on-one comparison of how our platform looks with respect to their platform. But I can still tell you the problem with their platform is still that the connection to the electrode is still a problem. They were having a problem of, since this is still a heavy device, it has certain momentum. So what happens is, if they want to start spinning and stop spinning in centrifugal microfluidics, you need to control it very precisely. Because of the weight, the control of speed was very much hampered. And the other problem was that the connection to the electrode was very poor. So that as you spin, the electrodes were, since the contact points were moving due to the weight, it created a lot of noise during the measurement. So they had a severe limitation of not able to spin more than 600 RPM. Sometimes for blood analysis, you need more than 2000 RPM for analysis, and that's not going to happen with this device. So compared to that, our device is just 127 grams. Our device is modular, so I will tell you more about modularity in the following slides. And we can rotate our disk really fast, more than 2,500 RPM. So we are not limited by anything. And the best thing is, look at the connectors here. So we have just anchored the connectors. It's not going to move. We just it's like the Lego bricks that kids play, the yellow colored stuff that they try to build, like the building blocks. So we just put the electrodes on top of the disk, and it has a specific holder in the disk design. It's engineered in such a way. There is no scope for this to move. So the noise is very, very low again. So combined with this, we demonstrated a superior device performance. And to show you how superior our performance is, So the green curves are from a commercial potentiostat, that's a big one, big machine. And the blue ones is from our machine, potentiostat on a disk. So we just did a cyclic voltammetry. For example, it's a very popular analytical technique. You can see how close it is to the commercial instrument. We are talking about an instrument that costs about 25 to 30 lakhs versus an instrument that we built only for 30,000 rupees. From a price point, it has nothing for comparison, but then you can see we can reach there with some minor variations. And this is more analysis of this sample here in a different aspect of data processing. In all possible ways, our potentiostat on disk is very, very close to commercial potentiostat, meaning that we can rely on the measurements that we get out of this. So that's a principal potentiostat on disk performance in a static mode. This is done without spinning. So then to increase the complexity, what we have done is we have made the concept modular. So we have always this platform, the bottom PCB constant. We have microfluidic disk, but then we can keep changing the connectors and look at two different connectors we have. One is single channel, the other is multi-channel, meaning a single channel, meaning we can measure only one. So we have eight detection units on the disk, and we can only measure one at a time as it spins. But when we say multi-channel, we can measure, in this case, this is a development board of one of the multi-channel potentiostats, multi-channel shields. We can actually have 4 channels measuring at the same time. So we don't have to make a new device entirely. We just have to swap the shield, put this shield, and then keep measuring 4 channels at the same time. All the softwares and stuff is embedded in the bottom part, so no problem. So this gives a superior capability. In terms of commercial instrument, you actually have to buy a separate instrument called multi-channel potentiostat, which is really, really expensive. And that's another reason why we had to do a custom-made device, because a device like this just doesn't exist anywhere. We just made it ourselves. So this device is based on Adreno Mega chip, actually. So it's an open architecture, and there are several resources available online of how to design a potentiostat. There are several open source circuit schematics, step-by-step procedure how you can actually make the device. I will come to that point a bit later. So to demonstrate the multi-channel capability, what we have done is we have chosen four different fluidics, and we are measuring 4 different channels. As the time goes by, we are measuring the current from the analyte as it flows over the electrode. You can see how consistent they are. So sometimes there is a difference. They should be exactly the same, but then you see some difference here. It's because of the speed in which the liquid flows on top of the electrode. Sometimes the flow of liquid is not consistent in all the 8 channels. In one channel it is faster, one channel is a little bit slow. It's due to fabrication problem. But then you can always you have a decent error bar, which is fine. So we constructed a calibration curve. So you can see that with increasing speed, there is increasing current because of increased mass transfer. So basically, for a given time, as the liquid is flowing faster, you will have more electrons going towards the sensing surface, and that is the reason why you have higher current for the same analyte. And that's what happens in terms of the flow measurements. So I can give you a little bit sneak peek of how the video looks like. So let's have a look at this video. That's a liquid loaded here. So once it starts spinning, the liquid, it's a metering chamber, and then the liquid is flowing. It's being pumped very, very slow. The liquid is slowly exhausting here. Yes, here we go. Here we are done. So basically, this disk is spinning about 2 hertz, and we are pumping the liquid just based on the centrifugal force. And the imaging is based on stroboscopic light. So there is a strobe light, it's like flashing, and then the camera is synced with this flash cycle, and then that's why you see like a video. There are several still images we stitch together and get a video like this. So to give a little bit perspective of what we did this disk for, these are several layers. So it has It's made of plastic. It's called a plastic called PMMA, polymethyl acrylate. Then you sort of, it's 1, 2, 3, 4, 5 layers. Sorry, 4 layers of PMMA. And then you stick each layer between the disc. You actually stick with the double-sided tape. It's basically like a double-sided tape, but then you have to cut them very precisely. Then there is an instrument called blade cutter, which does the job of cutting the channels very precisely. And then you have to assemble them together, and that's how the final disc will look like. So this is the fluidic schematics I was talking earlier. So in this project, what we did is we sort of have some filters here. We load the drug carriers, drug microcarriers into this, and we want to see the dissolution, how fast the drug from the microcarriers comes out. And that can be exactly monitored using our disk here. So one of the sample data output looks like this. So we start the experiment. Once we start spinning at 2 hertz, you can see the liquid starts flowing, and then we get increased current. So there is an electrochemical analyte. Instead of a drug, we actually put electrochemical analyte, and we measure the release of electrochemical analyte instead of a drug to show it as a proof of concept that we can do this in our project. So that's how, from the drug carrier, it gets dissolved, and then we can actually measure over the period of time. It's very decent dissolution curve here. So we were like, how can we make this much better? So we concluded this work as a paper, and then we were like, we need to, I was the primary user for this instrument. There were still several problems. For instance, we had the power was wireless power. So based on Kai charging, so just like the mobile chargers for wireless charging, the problem is that they should be very close to the device, the proximity. And then we usually have it very close, and sometimes we don't have enough power. We don't have enough power density to power the device. That has been a problem. And then the problem, then we don't have appropriate data transfer happening. Then the other problem is in terms of improving the circuit, because we have to handle this still manually. So this circuit components are exposed on the top. Since we were doing a development board, we were just adding wires and more resistors and capacitors on top. Sometimes when you manually handle, what happens is you sort of you disturb the connection. You break a contact somewhere, and then you'll be like, oh, this instrument is not working. What has happened? And then it takes a day or two to figure out what has happened. Then it will be like one capacitor somewhere disconnected. So to minimize that, we wanted to sort of make our circuit more simpler, to use more integrated chips, integrated circuits. So that was the focus, to make a simplified circuit, and then to further improve the modularity. So in our previous case, you might have seen for modularity. So this is it's like a breadboard. We sort of made our own breadboard in this shape. So these are proper PCBs fabricated, but then these are just like breadboards. So we actually manually soldered it. So this, it doesn't look pretty, but it does the job. So to make it very professional like this, that was the idea, to make it even better in the next generation device. So yes, this is what we achieved actually. So that's the next generation device. We sort of super simplified the circuit. Instead of having a wireless power supply, we actually integrated the battery under the bottom part of the circuit. It was just fantastic because it really reduced a lot of problems. And then the usability improved tremendously. So now with this, we sort of made a artificial gut on a disk case study. So we made a more complicated disk. So this is one of the research work which we performed when I was in Dublin City University in the mechanical engineering department. So what we do is basically we want to imitate, using microfluidics, we want to imitate the drug microcarriers going through the different parts of the intestine. You have different pH. So we want to see, we want different pH liquids to flow through the microcarriers. That was the concept with this microfluidic disk. It's sequential. We have different pH, 1, 2, 3, 4 different pH. We load the microcarriers here, and then we have sequential movement. I know it's very complicated. Let me show you a video. It's rather easier to see a video. So have a quick look. So there are 4 different pH here. So the first one is going to come here. We have a siphon valve. It comes, and then we have another valve. Then this one will open up now. It will fill up here. After this, there's a third one and then the fourth one. So on the right side, you can see the speed profile, how fast we are spinning over the time. So basically, we are like washing the microcarriers with different pH as it goes, and the electrochemical sensors are embedded right here, actually. So in this disk, we have not embedded the electrochemical sensor yet, but this is how we first develop the fluidics and then put the electrodes on top, because it's already a very complicated scheme, as you see. So this was possible only because we have because when you do a project, you should not have a lot of variables. Our instrument was always a problem to work, the previous generation, because of the practical difficulty I told earlier. So we had to first solve it down before we go into more complicated fluidics like this, which is exactly we achieved. So in terms of achieving the modularity, what we did was we replaced the shield. Why just electrochemical measurement? What else can we do? So then we sort of thought of an idea of having a microscope on the disk. So usually what you need is we actually image. You put a camera somewhere on top and see what's happening on the disk as it spins. But then we actually we change the shield in having a camera right on top of the disk and allow it to measure as it spins, actually. So what happens is it looks ridiculous how the system is, but it is so small. It's so small that we can actually put it inside an incubator. So incubator is a device that controls the temperature. So if you're growing cells, you need a very controlled environment. So you put the whole device with the camera into the incubator, and you can actually see the output, what's happening on the outside. So typically, what you do is you actually just put the device, put the microfluidic chip inside, and just to monitor, you actually take it out to a microscope and see, and then put it back inside. There is a lot of manual steps involved, but by doing this, you highly automate this process. This device is actually connected to internet, so you can sit at home and see whether your experiment is going or not, going right or not. So that's a pretty very fantastic way to actually use this modularity concept. So yeah, to conclude the platform of what we have developed, so it's a Potentiostat on a disk platform for real-time measurements in centrifugal microfluidics. We have shown integration of electrochemical sensors, and we have demonstrated modular capability in terms of multi-channel measurements and also the camera on the disk. So I guess I have a little bit more time. I can further go into future perspectives. So what else can we do? How fancy we can get? There is always never a stopping place. You can keep making it better. One aspect is to have impedance module. So there is something called impedance spectroscopy, electrochemical impedance spectroscopy, where you actually, so all these techniques for electrochemical measurement I've said so far, these are direct current measurements. So impedance module will be alternating current measurements, but that is technically more challenging because you need an amplifier, and then you need a lock-in amplifier for this process, or a frequency response analyzer. These are typically large machines. There are miniaturized versions of this, but then in that case, then you're limited in terms of what impedance range you can have. But nevertheless, it's a great idea to have an impedance module as one of the shields on the top. And we can do other optical measurements. Since we showed the camera capability, the next smart way to do is actually to demonstrate other imaging capability like fluorescence imaging, UV visible spectroscopy on top. So yes, for this paper, in terms of detection of for having electrochemical sensors on the disk. So this is our published paper in analytical chemistry. So that's the paper titled Modular Lightweight Wireless Potentiostat. And I'm so glad that our work was recognized as very interesting work, and we featured in the cover of this journal actually. So that's our device with different measurements. So analytical chemistry is one of the prestigious journals in the field. I'm glad that our work was featured in the front page. So basically, to conclude, in terms of what we talk about custom electronics, you see, I've given several use cases of when there was a problem, you try to solve it, and then you come up with a simple solution sometimes. Sometimes the solutions are complicated. The simplest solution is to buy the instrument. But sometimes you do not have such kind of instrument. You just have to make it. And that's exactly why custom electronics are exciting. And there is an explosive information available online in terms of how there is DIY kits. And of course, you guys are into electronics engineering, you know, Arduino programming, you do a lot of microcontroller programming. So this is great. So you can actually make, you are well positioned to make custom made devices. So in terms of what kind of device you should make is also a question that you should have. You should do something that has a benefit, that benefits somebody. So if you, typically if you ask people from maybe other department, if they are interested in making, if they need some other device which they cannot make themselves, well, it's great. Then you have a problem, then you have a solution. A very simple example I can give you is that we have several bridges in India with a particular height clearance, and there is always, you might have seen that there is a arch just before the bridge telling that this is the height of the bridge, do not cross. Well, always you still have some accidents, some truck hitting it and stopping it. You could come up with a very simple device that basically measures the height of the truck and gives a signal to the truck not to go, to have a traffic signal. So you can think of various electronics devices. For example, during the COVID times, there was a legal limitation of how many people can be in a store. You could have come up with a very simple human counter. You just need a LiDAR sensor to see whoever passes. You put a count, a plus minus, depending on the direction. You can have a double sensor also to know which direction the count is increasing. Then you know whether it's input, it's a entry or exit. So you define a problem, you define a solution, and you are well positioned to do it actually. So, and of course, I have to warn you that going down the path of making custom electronics is not easy. It's very time consuming. So usually it's a more fantastic team effort. You need a good overview, a good team to work along. So in principle, it could be great if your team has a composition of both hardware and software engineers, and especially an individual knowing both hardware and software will actually solve a lot of problems and make the development journey easier. On this regard, I could like you guys to be introduced to a particular journal called Hardware X. So this journal features a lot of work like this, where they actually give you a step-by-step instruction of how to construct custom electronics. People could have designed electronics for their projects in the lab, and there is a growing trend globally, like we should make devices and also share that information so that people in the other part of the world can also use it. So I could like you guys to stop a bit here and think of any device that you could potentially come up with if you can solve a problem. So what you have to do is just see whether you are capable to do it. What are the challenges? You need to do a quick assessment, how long it's going to take, and then you have to decide whether you really need to do it and just do it. So that this paper will this journal is really good in terms of inspiring you in terms of how people actually do the work and publish it. I can give you one example from our own group. For example, we have a paper which actually from our group which says about how to construct a setup with a humidifying chamber, auto sampler. The idea is to characterize, so there is a growing trend to characterize ingestible devices, like the small device that we take through the mouth with drug delivery and sensing in the like a pill capsule. And you want to, and usually the challenge is to measure how much it is stuck in the intestine walls, the mucus adhesion, to measure that there is no proper equipment. People don't have proper experimental control. So one of my colleague, Lucas Woud, he actually designed a setup where you can reliably measure this parameter. People were actually using like the vegetable cutting boards actually, and put the piece of intestine on top and put it in an angle and then see how it is flowing. It was a very let's say, not a very scientific setup, but this guy is really take this to a top-notch level. It controls temperature, humidity. It has certain lighting, and then it also has an auto sampler. So this point where it can actually, you can put tubes, small tubes here. So every 5 minutes or every 10 minutes, it can rotate and collect the sample. So you can later take it for sample analysis. So there are more examples. So people have come up with a programmable, low-cost, ultraviolet room disinfection device. I mean, during COVID times, you needed a lot of disinfection. And people are selling UV lamps, and they were like crazy expensive. And then people came up with this small device that you can just make it by yourself. It's super cheap. And you actually have a step-by-step instruction of how to do it. And then more examples like portable, low-cost, open-source wireless spectrophotometer for fast and reliable measurements. Usually spectrophotometers are in a ballpark figure of 3 lakh to 8 lakhs in the cost. You will do this in less than 20,000 rupees. You can construct a setup. Then more examples: an affordable and portable autonomous surface vehicle with obstacle avoidance for ocean monitoring. So it's just a small automated device that goes around to monitor the coastal part. It's a really small device. So yeah, there are plenty of examples. So there is a huge open source movement. So there is plenty of resource to learn. So in terms of also getting help, there are always people available. There are several literature that you could refer, and you can one day hopefully build your own device. So at this point, I could like to thank my group. So that's the whole group here. Our group Idun here, and then these are the guys involved in the project. Several electronics and biomedical engineers. It's a highly interdisciplinary group that we had to do this. Yes, and finally, thank you for your attention and for the invitation to talk in this seminar.
Thank you so much, sir. Thank you for delivering a detailed explanation on custom instrumentation. So you have started with simple examples so that our students can understand what is the need of the biomedical and how they can do the custom operations whenever they are developing any biomedical devices. So participants, if you have any queries, you can interact with the speaker, or you can share it in the chat box. Sir, you mentioned about that one journal that is Hardware X. Is it open source or is it free for you?
Very good question. Okay, let me. Yeah, so Hardware X. It has so. Okay, let's stop. Okay, I can stop sharing it for the moment. So the thing with Hardware X is that also for many of the Elsevier journals is that some of them are open source, some of them are not. So they started Elsevier and Science Directors particularly started a new concept called golden open access, where the researchers can choose if they want this to be published in the original version of the journal, or there is a X version which is usually open access. So some articles might be open access, some may not, but that should not be that should not worry you. You can always access the articles in many ways.
Yes, correct, sir. Sir, there is one more question from Shankar Rajendrian. The question is, if you want to go collaborative research with your team, is it possible? If yes, what would be the procedure?
So Shankar, I do not know what's your seniority level. Like, are you a master's, PhD, or?
Basically, I'm a professor and I collaborate with some masters.
Okay. Yes. So so usually our university is a public funded university. So that means there is so much level of transparency in who's involved in which projects, and you can see a bunch of information about all the researchers employed in our university. So after going through some of the works, if you're interested, you can write emails to them directly. So there is no, we don't have any standard operating procedure or something on this. It just if there is a synergy, so if you bring a certain expertise and that expertise is required here, so if it is mutually beneficial for both of us, yes, we can do that. So you just need to, yeah, you can, if you have something specific in your mind, you can write to me. We can take it forward depending on what is your requirement. Yeah.
Can you send your WhatsApp number and email number so that we can discuss over the phone?
Yes, I will share the contact details.
Yes. You can post it in the chat box. No, it will be very useful for us. Or I will post my number and you can send me the details, WhatsApp number. Because I'm seriously searching for the biomedical instruments to be developed, especially for glaucoma, and we have done some research. And of course, we have hospitals here, but we want to have international collaborative team to support this. And we have entire ethical team cleared, and we have done some publications, and we had very good results. But still, to make it as a product, I think it should be an international collaborative approach. Will be very fine for us. It's supposed to believe. In that case, I'm just approaching you people because I have seen your presentation. It's all with end product level approach. Of course, ours are only with research and feasibility, and we have got our what I can say results good, but still make it into the product level. I think we need some team from abroad because who are very much doing their research as a products. Of course, in India we do research, but we never make it as a product. So I'm accepting in that part.
Yes, I mean in terms of like end level product. So the use case is that. In general, I've observed, I don't know, maybe my observation is wrong, but what we need is interdepartment collaborative efforts in Indian universities in general. There are only few universities in India that actually do this. Many departments are very isolated. So electronics department, just electronics, working on electronics, not interacting with chemical engineering or biomedical engineering departments. Usually they have cross-disciplinary requirements. And also in terms of like student projects, when students are doing theses, like master thesis and bachelor thesis for that case, this is a fantastic case because you have a particular particular problem, and you have the capability from an electronics side, and from the biomedical or the electronics or from the chemical engineering side, you might have people with particular need for a particular instrument. It doesn't have to be a whole instrument. It can be a part of the instrument. So you can compartmentalize and you can break them in small parts and have them as thesis actually. So then in that case, you can, so the end product, what you say is more in terms of how useful it is. So it's not just doing project for the sake of doing it. So I believe that what you said about glaucoma, it's very relevant. So it's already an end product. So you're working on a very solid problem, and you should see it already as an end product, I think.
No, we want to develop an end product like home diagnostic equipment because glaucoma, it is not being detected. Of course, we have applied a magnetic property of the aqueous fluid and we collected and we did it. But of course, to come out with a product, really we need a support from the people from other countries because the product design and development needs a lot of experience and suggestions. That is what I'm expecting. And even when you go for funding in India, they ask for collaborative research. Who is the because nowadays, as you said rightly, in India, when a teacher is having a multidisciplinary degree, they are not been allowed to get into the teaching profession. But actually, they are missing a lot. Nowadays, even in DST and all government-funded projects, they are asking for multidisciplinary, multi-institutional, and international collaboration. And if that is the case, they are giving the funds. And that is what the reason we want to go for collaborative research. So mutually fund will be transferred.
I see. Sure, we can take this discussion on a separate channel. Feel free to write me.
I have posted my WhatsApp number. Please send me a message so that we can have a discussion. Of course, I have a lot of people from Brazil also. And I'm just communicating many people in this part. And I think who are like-minded people, as you said, a good team. I'm trying to frame a good team. And if possible, you are welcome to join our team.
Yes. Also, yeah. Regarding my affiliation with the group, I think so. I very recently changed my group from this group to another group actually. So we have to see how it works out. But you can always contact my old group. They are much in a better position.
Basically, I'm from Chennai. I don't have any contact with you. I think I got it from IEEE. I think I got this message from IEEE group and I joined it. And so you please send me your details in my WhatsApp number, which I posted to you.
Sure. We can take this discussion after this. Yeah, sure.
Thank you. Thank you very much. Thank you very much.
Thank you.
Thank you for the management giving you a good opportunity, making this international seminars and knowledge sharing technique. Thank you. It's a very big effort, and I think it's very useful for all the students. Thank you.
Yeah, thank you.
Thank you so much, sir. So now I request Varshini to continue the formal process. Any more questions from the audience? Okay, Varshini, can you continue?
Yes, sir. I thank Dr. Sriram T. Rajendran, postdoctoral researcher, Bioinnovation Institute, Denmark, for enlightening us on custom instrumentation for biomedical applications. From the webinar, we were enlightened about classical diagnostics, the point-of-care diagnostics, and the microtask systems. We were made aware of the evolution of analytical platforms, about how technology has evolved over time in the field of medicine. We were given an insight about more miniaturized sensors. We learned more about the concept of sensors, the electrochemical sensors, the biosensors, the electrochemical workstation, the potentiostat and its applications. We were made knowledgeable about the concept of microfluids, centrifugal microfluids, and the detection of centrifugal microfluids. We were also given an insight about the potentiostat on a disk, that is the POD performance, its modular capability, its multi-channel capability, and also the next generation POD. We were also given interesting information on certain case studies. The first case study was the case study on real-time model drug release from drug microcarriers. The second one was a case study on artificial gut on a disk. And the third one was a case study on cell growth monitoring. We were all motivated on doing new innovations using technologies. I thank you once again for your valuable time and for providing us lots of interesting facts and information, sir. Thank you, sir.
Thank you very much for the brief and summary of the talk, actually. So just for this, I heard from Dr. Venkatesha that the students might be asked questions based on the outcome of this seminar. So I just want to let you know that your focus should not be on specific case studies. It's more on the general concept of microfluidics and miniaturization. So this case study is too specific as a knowledge level. So don't go too deep on that. I just want you to understand the scope of this field, how things have happened, and what microfluidics are and sensors and how the integration challenges are. And that's already a great outcome for me if you can understand this very well. Thank you.
Thank you so much, sir. So we will take your words and so we will implement it. And we have our second speaker, Dr. Pramod KB. Good morning, sir. Good morning, Pramod, sir.
Hi, good morning. Good morning, Venkatesh. Can you hear me?
Yes, you are audible, sir. Varshini?
Yes, sir. Now we start off with the second session. I would call upon Apeksha G. Raj to introduce our next speaker, Dr. Pramod R., Division of Solid State Electronics, Department of Electrical Engineering, Uppsala University, Uppsala, Sweden.
Thank you, Varshini. The second speaker of today is Pramod KB Rangaya. Pramod KB Rangaya was born in Mysore, Karnataka in 1989. He is currently working as a researcher with the Microwaves in Medical Engineering Group, Division of Solid State Electronics, Department of Electrical Engineering Sciences, Angstrom Laboratory, Uppsala University, Sweden. He got his PhD degree from Jain University, Bangalore in Electronics Engineering. He received his BE degree in Electronics and Communication from Dr. Ambedkar Institute of Technology, Bangalore in 2010. MTech degree in RF Communication from Jain University, Bangalore in 2012. and worked as an RF design trainee at Icon Design and Automation Private Limited and as a visiting research scholar at University of Concordia, Montreal, Quebec, Canada. He is a life member of IEEE, ISTE, and IETE. He is also a regular peer reviewer for various prestigious international journals such as MBPI, InterScience Publishers, ASTESJ, and IJARIIE. His research includes design, characterization, and optimization of RF passive devices, broad level tuning and optimization of matching networks, low noise amplifier, power amplifier, circuit linearization, and high efficiency design techniques, circuit instability, and strategies. Over to you, sir, and thank you for accepting our invitation.
Hello. Hi, thank you for the introduction. Can I start with the session?
Yes, sir. You can start with the session.
Okay. Just, can you able to see my screen? I am not able to share the screen. It's not allowed.
One minute.
So I think I need to be a presenter. I joined as an
Sir, you can present it now. Can you check it once?
yes, sir. Just a minute. No, still it's not showing the share option. Presentation. Your enters this has to be I think vendors are like I think you need to give an access for me. It is like
Sir, we have given the access, so you can check in the bottom. There will be present now option.
Yes, I have pressed with an share entire screen actually.
Yes, you can select that.
Yes, but it's not showing the share option. Only cancel option is showing.
No, you can select that screen. Then it will show. That window you can select.
Yeah. Okay, I will make that window then. Okay. Okay, like okay, I got it. Okay, can you able to see my screen? Hello.
Yes, it is loading, sir.
Okay.
Yeah, now it is visible.
Okay, thank you. Thank you for the good introduction, and thank you for Cyber Institute of Technology, and thanks to Winter and management. Today we'll be talking about the design of microsensor for biomedical application. Generally, my talk will be more with the linear and non-linear models which use for the design thing. So a short introduction has been given. Just I like to introduce myself with what I does actually with respect to electronics. I does with the design and characterization and optimization of RF active and passive devices, especially with coupler, low noise amplifier, power amplifier, and other microcircuitry. And now I'm more working towards with the sensor techniques and also RF and micro interfaces with the devices. And I does with the board level tuning and optimization of matching circuits and devices like low noise amplifier, oscillator, mixer, power amplifier, and circuit linearization and high efficiency design technique, and making the circuit with stabilization and preparing a design topology and strategies. I work on this kind of a thing. So regarding my qualification, yes, it has been given. And I like to talk about Uppsala University. Uppsala University is one of the oldest in the Scandinavian region of Europe, and it is having a good ranking, like 63 with the academic ranking, with the Schengen ranking, and with the QS2 it is having 112, and we have got the higher education with 88. And we do have more than 40,000 students at 11 different campuses area, and more than 16,000 master students, and it is very one of the oldest, and is founded in 14th century, and we do have 8 Nobel Prize for this university, and more than 3,000 teachers and researchers. I'm one among them, and we do have more than 2,500 PhD students, and more than 6,000 peer-reviewed scientific publication till 2017. So I like to, before starting with my content, going for the design and other stuff, I like to show about what kind of work we does here. So just a moment. So currently we are working on various projects. This is one of the projects called Syringe Pump. What we does is here, we will be identifying the burn depth and burn area, and also the depth of the burn, and the various, we will classify that, and we will be providing with various information things. So this project has started from 2.5 years back. We do have a lot of consortium members. So Uppsala University is leading with this, and we do have an hospital for academics with it. There is an Uppsala University hospital. Those doctors provide us an physiological information and biological information related to how we need to prepare a sensor. And there is a company called ITON with this. So they provide us the technique with making an cloud computing, and also preparing our data and preparing an application for the end user to use our sensor in a proper way. And Data Matters, this company, they deals with the statistical analysis, and rest of the company, they provide us 3D models, and Informatics is provide an service for internet access and also IoT management. Why I'm telling about this is whenever we talk about any of the project, we require a big consortium, so that if we are multidisciplinary activities will happen, and then we'll be making with a very good innovations. And I do work on Syntech project. This is making a circuit. We have got a rigid circuit. In this project, we make all the electronics into a stretchable and flexible, and it will function much similar to that, and it will be biocompatible. Say about this is on small sensor. This is this has printed on a special PDMS layer, and we use halogen materials and also some of the liquid metals for the fabrication, and we will be simulating that kind of the sensor, and we will be interfacing with the small IoT modules, or we use from the module from the ST microcontrollers like Morphia boards for the communication inside the body and outside the body, that the in-body communication, off-body communication. This is one project, and we do have, you can just follow up all these websites, it is available, and you can follow up us with LinkedIn and many other social networks. And we do have another, this project has been recently finished. This is BDOS, this is a bone density analysis system. What we do is here also we do have a collaboration, and recently with the last presentation, I asked that people ask for the collaboration. So we have got a collaboration with Amrita University from South India. So that is possible, if the university collaborations and everything, if technically if they're matching, if they prepare with the roles and work packages and tasks, what they can make or contribute for the project, definitely that will happen. So just I want to show this, the consortium happens with international, with various universities. And since we work on a biomedical sensor, a microsensor, we will be having always our main collaborators will be more with the doctors in our hospital. So we have got more than 11 to 12 different hospitals across the world. So they provide us a sample, and they help us in the clinical trial and animal trial and many other things. And recently, this project called BDOS, recently it has started. So this is like interfacing the brain towards to the end. So what is this? Our objective of this is like we have got like many consortium. They are working towards this for us, and Uppsala University is leading. Professor Robin Augustine is leading this. Is one of the well-known professor from Uppsala University. And our objective of this project is that we will be taking a signal from the brain, from motor cortex, and we will be sending that signals to the fat channel towards the arm, and we will be making this arm more realistic. And we will be having we will be having an artificial skin that can sense the object, and that will send the information again back to the fat IBC communication, and it will ask the brain to react. Recently we have started, and it is a very big consortium. We have got like artificial neural network computing people and machine learning algorithm, and we have got biometronic experts in this project, and preparing an artificial skin experts are there. And mainly we work on like fat IBC. That means like we will be communicating the things with the fat. So just I introduce what kind of a work we does here. Now I'll straight away jump to one of our recent work. Can you able to see my slides now?
Yes, sir.
Can you able to see my slides now? Yeah. Slide one. I'll leave the link up to this. Okay, I will.
Sir, you can present it once again.
Oh, yes. Yes. So entire screen is not happening. That's why I need to shift. Okay. Okay. Can you able to see slides now? Okay.
Yes, it is loading, sir. Your slides are visible.
Oh, okay. This is our one of our latest work which we have made here. So in this work, what we have done is that we have made attempt to detect the burn depth and degree of burn by clustering and by making a diameter profile. And also those things we are like to correlate with the color profile. So about the SensePump project recently, just now I shown the website. What is this as a medtech R&D project from the European Union program from Eurostar to develop an advanced early detection diagnostic tool, non-invasive tool for the clinical usage. So why we make this kind of application is the early invention in the burn injuries will save the life. And if you have from the WHO and the various burn association data, many people have died because of more than like a 3rd degree or 4th degree burn in proper treatment. So we will be detecting the burn depth in a very earlier stage, and we will advise the doctor in a very proper with the 3D view, and also we will be accurately making analysis. This is the depth of the burn. So that will be helping the doctor to choose the right treatment for the patient. So this innovations, it is not just about the microwave. We will deal with the micro sensing part, and apart from the microwave, we have got 2 more innovations in this project. We have come up with a non-invasive microwave depth sensor. You can see here the sensor which have been made. This is a very specialized sensor which consists of a split resonator inside that. That has been connected with a mini VNA. And to compute that, we will be using a simple Raspberry Pi, and we will be using for power backup we will be making. And this is completely a system thing. And to visualize for the doctor whether the burn depth is what is the burn depth and all. So we have to come up with then surface 3D imaging. So our sensor data will be interfaced with that 3D imaging, so that the doctor will have a proper view that which body part and what is the depth of that, and whether it has penetrated towards this fat or muscle, or whether the burn is reached to the bone level. There is a 5th degree burn. So those things can be easily visualized here. And applications will be provided because like most of them, it is easy for any of the user to see all the measured data through the application. We have come up with an application for Android and also iOS, and also it can work with the web website also. And we will be providing a separate channel for the doctors for usage, and you can select the number of sensors, and you can check his performance. So when we talk about non-invasive microsensors, say invasive in the sense we need to go with an implantable things. So when in the burn patient is there, implantable things are not possible. Like we already tissues have been damaged. We have to take care in a proper way that, and also sensors should be biocompatible. So what we have to do is that we have to make with the non-invasive thing. That means we have to see that how to find out what are the properties of the tissue and how to detect the burn depth. So what we have chosen, that means to detect all those things, we have chosen parameters like permittivity parameters. So we can to design that, we have decided about first we have to make a dietary profiling, and then we will come up with a sensor. So what we have done in this work is that we have taken an ex vivo tissues from the hospital. So instead of making as a surgical waste, we bought it in the micro lab and we have made a dietary profiling. So that is called like a sampling and data manipulation. To come up with any of the sensor, first we have to take what we are going to use, and similar to that, we have to prepare and mimic the tissues like a phantoms and all. And we have to test the performance on the ex vivo tissues and the phantoms, and later on with animal trial and with the human trial. So in this technique, to come up with the sensor, we have looked for the dietary profiling. What we have to do first, we have to make a proof of concept saying that on dietary profiling can detect the burn variation in the skin. For that, a study has been conducted, and for that, what we have made is that we have collected ex vivo tissues from the from the hospital. We have divided that into a number of sectors with sequential and also with random session. And every sectors we have characterized the permittivity with the repetition and the thing. For our for the comparison, we have got an IFAC data. This is a very standard database across the world from Italy. So they provide the dietary profile properties of the body tissue for the various things, but they are not provided for the burn level. So we have added our database to the research contribution. We have provided a database, and also we have made a cloud computing, and we have come up with an algorithm to detect and correlate our sensor data with the burn degree. So procedure comes like this: like once we receive the sample, it takes every sample has to be assessed with at least like 8 to 10 hours. It happens. That means we will collect the tissue. We will not be cleaning immediately. We will be making, and we will remove the breast stains, and we will sectorize manually, and we will go on making a dietary profiling of that area, and we will be saving those data, and then we will be proceeding for clustering and other application. So at that time it was like 16 procedure. Now we have completed more than like almost 22 surgical procedure, and we have collected more than 60 ex vivo tissue samples, and we have characterized that. And in this work, like since published in last year, so at the time it was like 16 surgical samples and 30 ex vivo tissues. So in this work, what we are liking to correlate is that we will make one dietary profiling and also color profiling. We like to correlate that. So, and also I will talk about like why we have made this and why we have taken slightly, we have shared our sensor data with another domain. So what we have done is that to characterize this based on the permittive changes, and we will see whether the burn variation can be seen with respect to permittive changes. And we have done manual sectoring in this case. And for statistic analysis, we have used some of the tools like ANOVA and K-mean algorithm. And we have made the clustering based on that characterization. And another side, we have got a color profiling. So we have analyzed the color variation in the burnt skin, and we have made with image processing algorithm. We based on the intensity range and various, we have decided in every cluster with centered value, And for the evaluation, we have used the zeolite analysis, and we have made the clustering of the various color variation of the burnt tissue. So how we will characterize this data profiling in our lab is we do have slim probe kit from the Keysight. So we have got many kinds of probes. We have choose for this experiment called slim probe. Slim probe is good to assess the things for liquid and also semi-solid. So we come to know that physically like this burn schemes or like a semi-solid. So we sort of like to start with this slim probe for our experiment. Apart from that, we do have many other probes called as an performance probe, temperature probe, and many other probes. And this is not the only method. We have got a few other methods like ring resonators methods. Based on that, we can assess the dielectric property. But we have chosen this because it can give a wide range of frequency. It's starting from 500 megahertz to 50 gigahertz, and it's non-destructive thing. That means like since microwave is ionizing, it will come with a non-ionizing field, so it will not damage the tissue. And even the probe which we are using, it will not damage the tissue. That is very small, and we not to insert it, and at least even it can characterize up to like 2 mm. So it's a good thing for us. And apart from dielectric profiling, we do have characterized based on the conductivity and loss tangent. So these are the electrical parameters are very important when we are coming with the sensor. When we are designing any of the sensor, we have to make a 3D modeling of this tissue layers, and we have to test the performance. We have to simulate our sensor topology on that, and then we have to make the trials on the phantom and animal trial and clinical trial. This is the procedure. So dielectric profiling, what we have done, we have collected the ex vivo sample tissues, and we have done manually sectoring, and we have measured dielectric permittivity, and we made certain statistical analysis and with ANOVA and everything. You can see that our setups look like this. We use a field fox, that is a vector network analyzer, and the portable and it is having very good dynamic range, and it is a very good device which to see the reflection coefficients value. So reflection coefficient values will be converted into a dielectric permittivity based on the software that is provided from the Keysight, and we have used a slim probe for this experiment. So this is like just as a coaxial line which will which will send the micro signal from the center cable, and it will and a reflected signal it will be calibrating, and then it based on that reflection coefficient will be calculated, and reflection coefficient will be converted into dielectric permittivity based on lot of numerical calculation. And we have interfaced that with the LAN, and every time we use him same thing, and we do have IO Connect from the Keysight. We use that software for interface, and for the conversion we have used the material measurement software. So once we take ex vivo tissue, this is ex vivo tissue from the human, which is it's from lower extrema region, and it's from male. And this one from the doctor, we will have a clinical opinion that what is the kind of a burn. So in a modern technique, we do have techniques called a superficial burn, deep burn, partial burn, full thickness burn. And then is like previously we used to make it degree 1, 2, 3, 4, and all. 3rd degree burn, 4th degree burn, and 5th degree burn. 5th degree burn is completely it is like skin, muscle, fat. It's completely burned. We can see the bone. That will not be exist at that time. The chances of treatment is very difficult. We will concentrate more on full thickness burn. So that we will advise the doctor that how much depth he can remove, and he can go for plastic surgery. That means we need to identify what is the depth of the burn. So what we have done is that we have taken ex vivo tissue already, which has been like operated, and we have done a manual sectoring of those tissue. And this is sequentially made. That means it's having more than 116 sectors. And every sectors we will be characterizing with the data profiling and with the 3 repetitions, sometimes even 5 repetitions. And we will take that, the average of that we'll say. And we have introduced in this work a novel concept called as an permittivity-based microimaging. Generally, microimaging means it's based on the electric field, and whatever we are sending the radiation that we will be looking, we will be using an antenna arrays and we will be making a microimaging. But this is quite different from general microimaging. So we have coined the word for them permittivity-based microimaging. So what we have done is that we have made a manual sectoring. So we have assigned and rows and columns with a plot. We have assigned the permittivity value, average permittivity value of particular frequency, and we have given for that. And we have normalized that with an IFAC data. That means like with the normal skin value is of 38. So we have normalized all the value to the 38. That means you cannot see skill more than 38. That means if it's lesser than that, means it's more with the bun. That's what we like to prove in this work. So we have made that, and we have correlate with our sample, and we have just given assigned the color from like less quite healthy skin with yellow color and which is damaged with a dark blue color. So this we have made this will be giving us an idea to prepare a 3D models for sensor. So once we come up with a sensor, this will allow us, like we will prepare and corresponding data profiling and permittivity based imaging. And this will be an mask and map on the 3D model, so that when we keep our sensor on the human, so that and doctor can see the 3D image and he can just rotate those things, 3D models, and he can see an appropriate depth of the burn. So based on statistical analysis, we have made generally we have made more than 60 samples. So what we have made is that we have made a cluster. We made a group like degree 1, degree 2, degree 3, and degree 4, and corresponding sectors we have made, and we have found the mean value and standard deviation, median, and some confidence level or low on. So we are able to get 95% confidence level with a proper clustering of the data. So this clusters will be correlated with the degree of the burn. So degree 1 will be corresponding with the cluster 1, and that means lower the burn we have grouped with the cluster 1, and higher with the burn depth we have made as a cluster 5. So you can see corresponding permittivity value, it has been and change for the 500 megahertz frequency from 48 to 10. That means this has given us a proof of concept that yes, burn degree can be analyzed based on that permittivity, so that we can start designing a sensor by change of this. For designing any of the sensor, first we have to look at it, what is the key parameters, electrical parameters which need to be identified, and based on that our sensors has to be prepared. If it is like a key parameter is based on the fluid thing, then we have to design our sensor based on the fluid. If the key parameter is based on a permittivity, we have to design based on the permittivity changes. If the key parameter is based on just reflection coefficient, S1 or resonance change shift, so we have to make it that. So we have to identify what is the right parameters to make it, and then we have to build our sensor. So this is the technique. What we need to start with that. So we have made a certain statistical analysis grouping with that, and we have made some cluster analysis with ANOVA. This is at one side, and another side, what we have made is like for 3D modeling, we have to see the color variations also, and we have to make it. So we thought of making a correlation, and this becomes very easy when the patient is with a white skin. And if the dark skin, then it will be quite difficult. At that time, we have to use not just with the camera, we have to use thermal imaging or any other imaging, and then that has to be correlated. So this is done with a simple photographic, a simple image. So that image we have made with the 2-level clustering, and then we have made with the 5-level clustering. And you can see the darker region is like more burn, and there is a less light intensity colors, or like with the less degree burn. And this we have correlated with the pixels with the manually made the clustering for the permittivity imaging. So this permittivity imaging and color profiling has been like in the algorithm we have made a comparison. So that will happen for most of the case. It will be matching well, apart from the dark skin people. So for this algorithm, also we have used a k-mean algorithm, and that also k-mean algorithm because we are going to match these two parameters together. And it's like for a doctor, how we identify without touching. If you want to identify certain things, he will detect the burned up with the color only. So we have made like, and then he will look for some of the techniques, like modern techniques with punch bioscopy and blood samples and other things. So that is a different thing. But basically, first you will look with visualization without touching a person what he can do. This basic algorithm can do that. And when he is testing that one with the punch bioscopy and other techniques and all, like insertion design, which are like invasive technique. So for that, our technique provides a non-invasive solution for that with this diet to change. So in this one, in image, we have taken a dimensional matrix and we have made a clustering, and we have found a centroid for every clusters, and the distance between the centers have been like cluster we have made, and we have made like silhouette analysis for the evaluation, and the pixels are falling in a better clusters, and we have made with that, and we have come with that, and we have found very good clustering form, like silhouette values varies from -1 to 1, and the good value means it should be like ideal value is 1, and all our pixels values are more than 0. So we found a very good clustering in this based on the equivalent distance metric, and we have analyzed that, and we have compared. So this is one small work we have done as a part of an Sandstone project. And after this, we have made many other things, and we have recently made few novelty search, and we are going to file few patents based on our sensor recently we have made. So the sensor which I have shown now is like and recently published, and it is open for the thing, and so that's why I posted with that. So I like to show a few more sensor. Just a moment. Just a moment. So we do have so I like to show another sensor we designed for the BDAS project. So that is for bone density analysis. Just, can you able to see my screen? Okay. So, hello. Yes, like in this project, this is like this is one of the recently closed project. So what we have done is that we have come up with a micro sensor for bone mineral density things we like to identify. So in this one, like this is part of two projects. One is the comfort and BDAS. So what is this objective of this one is like we prepare an clinical domain models. That means like we will take some of the ex vivo and also recently operated patients' data, and we will take that one, what are the growth stages, and we have taken in earlier talk what I have given like for sense burn, how we have made like 5-degree burn. Here we have taken an interval of 4 stages. One is like a stage 1 is of post-operative defect, and second stage is of formation of bone during the durometers, and stage 3 is of bone layer formation when it happens, that one, and stage 4 is of provisioning growth healing defects. These are different 4 stages which will come when the patient is going to operate with that. So to identify that, we have taken this kind of we don't have any 3D models. We need to prepare that. But before going to that, we have collected a sufficient electrical characterization has been done during that operation. And also, so the stage-wise, we have used our sensor and we have checked its performance and their resonance frequency changes we have made, and we have made a better database. And one more is called low extreme factor in this one. Like this also, it happens in a very older age. Here also, there are 4 different stages. And here we have made the implantable thing. That means we have got an specialized probe which can be inserted with a small hole towards that, and we will characterize at the joint level and other things. So with the from the above the discharge level to the pelvic thing, we have characterized for the many patients by using a non-invasive probes and also invasive probes. And for all 4 stages, we have collected a sufficient physiological information, and also we have come up with some of the like stretchable, flexible sensors for this. So what is this technology? We will be generally used with center frequency 2.45 gigahertz because for the ISM band for similar, because we'll get a lot of support for like we will have a lot of modules which work on this frequency, so that we can make a lot of our sensor more automated. So that's why. So if you are choosing any other frequency apart from that, then it will be quite difficult. So most of our sensors will fall in 2.45 gigahertz and 5.8 gigahertz frequency. And we will be preparing an artificial model, that means mimicking the tissue phantoms. So and we characterize based on the EM structures, and we use relative permittivity and conductivity characterization will be done, and even also loss transient will be characterizing. Based on that, we will mimic the tissues. And for sensor development, especially for this sensor development, I like to show how we have made. So what we make is like sensors is prepared with like micro. This is just simple SMA connector, and we do have different things. One is of ring. That is like we'll say split ring for the high impedance capacity things, and a series line which acts as a resistance for us. And for inducting effects, we will make it like we will make with the T-shaped feeder we have made, and the feed will go for this T-shape, and this will reflect back. And this gap, the split ring, it will act as a capacitor for us. This will become an high impedance. So this will create a resonance for us, and this will be perfectly matched for the 2.45 gigahertz in the air, and also it has to penetrate towards the human tissues. So that is a major challenge for us. So when we consider when we prepare any of the non-invasive sensor, so that means if we can prepare easily a sensor by implanting certain things. So that is quite easy. But when we are looking with the non-invasive thing, we have to think about, because skin is a very lossy medium. So we have to prepare a micro sensor exactly should match for the skin thing. So we will prepare a different kind of a sensor for different body parts, because skin thickness varies for the body parts. Say for the distal region is different, for trunchous region is different, for the thigh it is different, for the face also, for the lips and for fingers, skin thicknesses varies. So we have to come up with an appropriate sensor for the body part. And also we need to see about like fat. Fat is a very good conducting medium for very good for the micro communication. Whereas muscle is again lossy. So there are like 3 different human model that is very challenging for us to come up with a sensor. So for any disorder, we have to choose an appropriate topology how we will come up with a sensor, and corresponding dielectric and connectivity of those layers has to be simulated in some of the EDA tools, and then we have to test those things on a phantom, and then we have to go for an animal trial and clinical trial. So what we do is that we will take not micro imaging. We will have a lot of technique, MRI techniques, which already imaging has been done by the doctors for the different patients. We will collect that, and we will prepare, and similarly and tissues and we will check on that. Say about this one, like we will have a several app for this. So based on that, we will see a layer wise for all the views. It is not about like horizontal and vertical. We will take for all the views because we are going to make in 3D modeling for that. So we will consider that, and we will prepare and skin, fat, muscle, and bone. What kind of things is required? We will prepare a 3D models, and we will assign the electrical characteristics of that, and we will simulate that. And then we will come up with a sensor, and we will test not only electrical field variation and also SAR effects, because our sensor, once it is there, we need to follow some of the European standards and US and other standards. So they say that 1.6 like watt per kilo if they make as a SAR effects. So we need to make with that. And the SAR measurements has to be certified. And for the lower thing, if you are operating like lesser than 30 dBm power for the sensor, so we need to make it, because already even though we make this as an class B as well as regulations, we need to make all those things. SAR evaluation and electrical evaluation is must. So what we have to do is that we have to simulate in a such a way that if we are targeted with a bone, so if you are looking for the characteristic of a bone, then our radiation, you can see that the radiation should go and this should come to the bone level more, and it has to characterize that. So even we will make with not only like just and planar phantoms, we will make with cylindrical phantoms also, and we will place our sensor on that, and we will characterize. So first we will simulate so that major field has to infer towards that region, and then we will look what are the changes based on the different disorders. So this is how we have to design a sensor. We have to look for it, because if you are come up with some of the resonators with an even the higher power, it's not radiating properly. It is most of the things, most of the energy is consumed, or else it is finished by the skin and fat layer, means it is not reaching for the bone properly, means our sensor technique is not like an antenna thing. It's not about the giving them more direction and directivity, increasing directivity and pushing the signal towards certain direction. Sensor things are very important, where that we need to infringe the field for which kind of a disorder we are planning, and the radiation and E field should come on those regions, and then we have to see what's happening in that region. So that's how the sensor has to be designed. So basically, I'm not very good sensor designer, because we do have specialized sensor designer in our university. My work is more for the RF circuitry part and interfacing with that. But for any interface, I need to look for that, and I need to optimize the sensor based on what kind of a matching circuit I make. If the sensor is not matched properly for the automating or any kind of I design balloon structure for this, and also I come up with a coupler and many other things. If the sensor need to be optimized, that both can make both should be matched properly, so that signal maximum power will go towards that region, or else it will fail. So we need to optimize. That means we have to work hand in hand for both the like the sensor and also RF circuit part. So what we does in this one, for the testing purpose, we have prepared and phantoms with the skin, fat, muscle, and bone, and we have made some of the metallic implants to see whether the reflection is happening properly. And we use some of the initially we prepare and 2 mm skin thickness, because average skin thickness and average fat thickness between like 5 to 10 mm, and muscle is of 25 mm, and the bone is of 40 mm. And we will test our sensor, and we will check whether the radiation is pending towards the bone and everything. And most of our sensors are like with a single port. That means one port. We will be looking at the return loss values. That means the S11 curves. So what we make is that we will measure that the resonance frequency shift in the thing, and we will look for very good shape factor in order to get an appropriate, very sharp resonance frequency for that, and we will simulate it for the cylindrical and square phantom, and we will measure. So we will simulate it, and we will measure on the phantoms. And of course, like this will not match exactly, because like simulations will get exactly 2 mm, exactly 2 mm skin thickness will happen. And when we fabricate that, and we cannot frame in a realistic exactly 2 mm of skin thickness, or say about 10 mm of pad thickness, means we cannot fabricate exactly for that same thickness. That's why the resonance frequency changes happens. And also realistic things, because we will consider, like for a sensor, we consider only dielectric permittivity and loss tangent and conductivity. Sometimes more than that, electrical parameters varies, and also like testing and fabricating efficiency and other things. So, and also we prepared an oval phantom, which is like a skull. It is a skull, human skull, and we have tested our sensor on those things. And we have simulated similar thing in a 3D models, and we have mimicked that in a lab. And we have prepared an oval phantom, and we have checked the performance. And we created in that phantom few defects, and bone density we have changed. And based on that, the defects from 0 mm to 8 mm we have made it. And healing 0 mm is a complete heal. We have changed the bone density of the phantom, and we have calculated. And followed by that, we have made a man for the human head without implant. So we have tried with that, and stepwise, first we make with an planar phantoms, and followed by that oval, which is of similar like human head, and then followed by that human head directly, and we have seen the changes, resonant frequency, how it's reacting. And if I'm talking about why I posted this slide, is like when we see about any theoretical things, we have to look for like why we study in our academics about transmission line theory or this thing and all. Yes, it is like for the basic things to understand like how we have giving the source, and one side is the like brain is the load for us actually, because it absorbs more. So all our layers will come side by side, the skin, skull, all this thing. Because for head portion we don't get any fat actually. Skin, after skin directly skull will come. There will be no fat or muscle in the head portion. So if it is for the other body parts, we have to consider those things. So transmission line theory, when we study in our academics, we have to see that one. Like this is one of the application, designing and sensor is one of the application. Even though like we may not understand much about mathematically how it works, we have got several EDA tools to support that. But functionally, we should know that few concepts, theoretical concepts before designing in any of the sensors. And we have come up with many sensors, like we have got like this sensors which have boosted like a color with similar topology. Probe 1 is of like is multi-ring technology. So we have printed many this thing, and this is for discharge region. That means before like near knee for discharge region for the leg. And one more like probe, second one is for the discharge region, and is based on the split ring resonator. And third one is for the thigh, that is also based on split ring resonator. And for truncation region also we have used the split ring resonator. This is the back view and also front view you can see. And we will use like for biocompatible things, we will use some of the superstrate above the metal deposition. And finally we will match certain things, and we will make a biocompatible PDMS layer we will grow on that sensor, and then we will go for a clinical trial. And these are the like just I posted some of the physical dimension and how we prepare. We use a different substrate in our lab. We have kept more than 150 different kind of a substrate. We use most of the from the Roger company, and we will just first we'll start with FR4 easily available and normally used as substrate, and then we will switch that with some of other substrates. And recently for less loss tangent things and all, we use Iconic material. So those are very specialized materials. It makes our sensor design quite easy. So, and we work on different resonance frequency. Most of the time we'll go with the 2.45 gigahertz and 5.8 gigahertz. Sometimes if it is like based on different physiological parameters for the different disorders, we switch our frequency and we will calculate, because in a research level we cannot stick with a single frequency. When we are interfacing, what we do is that we will save those data in a local device and then we'll transmit. So then if it is even resonance frequency doesn't matters for us. So this is about the thing, and we have performed few clinical trials. This is for distal region, and we identified a few promising results, and for left fracture femur, and how its resonance frequency change generally is the right shift. So we have prepared few algorithms to make software algorithm to identify the peaks of those stream data, and also to judge and to provide for the doctors like what is the fracture or bone growth in that particular disorder. So like this can be identified with our sensor, and we do have several data and several volunteers discussing. And most of the time for the volunteers, we will take generally there will be a lot of difference between the gender, like a male and female, like the tissue thicknesses varies. That is also very challenge for us, and the weight varies, and especially body mass index is a very key things. We need to see body mass index, and based on that we have to simulation models as to make. So generally we will make an average above average body mass index, and below average athletic. So we will prepare certain athletic and obese phantoms initially, and we will make it. And age factors also matters, because like especially for the muscle quality. So sarcopenia patients, if we are measuring on sarcopenia patients, for them it will be quite very difficult for us to analyze, because what we are thinking, say about at 2.45 gigahertz, if the diatric constant is of like 58 muscle per muscle, that will decrease actually for sarcopenia patient. And also bone densities varies with the human to human, race to race. And so these are some of the channels. For the healthy things only varies. So we require more clinical trial for the improvisation of the sensor. So these are some of the basic things we consider for the clinical trial, and we will make it. So we have seen like for the thigh and distal interventional region, and we have made a much more number of clinical trials, and we have evaluated, and we got few approved for certain. We got ethical approval for the clinical trial for our sensors, which we make it, and we have passed with the regulatory acts, and it is not with the commercial product. It is as an R&D level product. And we do have come up with few patents also here, like a few are in a pipelining for our sensors and other things. So like these are very, there's a 1.5 year before story. It is like, it is not latest, but apart from this, we have progressed much more, and we have not come with as an article or anything, because like first we will target with the patents, and then we will come with an article. Once this article is published, then I am allowed to do my other thing. And just for like, I like to end my talk by showing some of the softwares which are useful, and for especially those who are what like they have to work on numerous things, I like to say. So I will show just the steps. What are those steps? Like initially, whatever you design for any micro things, we should have a basic idea what we are going to do, and that has to be on paper, and we have to choose what are the circuit related techniques we are going to use, and followed by that we have to prepare the 3D models, and we have to work on those things, and we have to make some RF simulations, and based on that we have to make a machine prototype. And we do make machine prototype for a micro sensor, means we will fabricate the sensor, and also we need to fabricate phantoms, because that is the two things. And the prototype testing has to be made with a very good appropriate anechoic chamber. So what we have to do is like for general micro this thing, we can use a bigger version of an anechoic chamber. For medical related thing, we have recently made one semi-shielded box for the phantoms, which is very good, and it can work up to 18 gigahertz. So that is much we with a lot of expenditure we have made that Anakin chamber. I lead with that and I I prepared the Anakin chamber for that for phantom experiment. And after that, the concept of roll comes. Apart from this, we do have a lot of SAR measurements and other things, and it's very expensive things for the testing thing. So what we do is that if we get approved and if it is like our conceptually basic concept is very correct, then our simulations will be going well, and then mission prototype will work. So we spend more time in 3D modeling or RF simulation because that is a very important step. If we make those steps after that, if you are invested more money and time for the machine prototype or prototype testing, so we will be losing our time. We will be wasting our time on resource. So I like to say, as a micro circuit designer, for me, very important phase is 3D model and RF testing. And for every stage, for any software, there will be data files and netlist will be created, data expressions, and there's a loop every time we have to optimize and improve. So basic concept means for us, sensor design means we have to collect all the ex vivo sample tissues and patient tissues and some of the animal related data that we have to take, and we have to prepare the 3D models and our simulation models. So for any of the modeling on the things, see, we have to have three basic ideas. What is that? Frequency domain measurements, time domain measurements, and modulation thing. And what are those models, sophisticated models you can use for our simulation? This has to be there. And fusion of all those things like modulation schemes, all those things should be there for you. And just I will skip, and I like to show like EM structure. All our sensors has to be made with EM structure simulations. So from 2D to 3D, there are various model simulations like cross-sectional solvers or transmission line or built-in models. These are very fast simulators. Few tools makes it, but accuracy of those things are very less. And if you are going with there, if you are looking with some of the PhD and the thesis which have come up from past 1 or 2 decades on things about the micrometers, they work on the methods of one technique and eigenvalue. Those are in between like 2D and 3D. So those are good for the some of the circuitry part if you are working on planar interconnect and patch and on other circuit level verification. For that it is okay. For the sensor, this thing actual 3D simulations has to be done. That means like FEM technique, FTTD, BM. These are some of the technical and fast solver techniques has to be used, and that demands a very big gigantic RAM and very good processor and very good machines to simulate all those things. So I like to talk about for any sensor technology or this thing and all, 3D simulations are very important. So if I'm talking about FEM technique, means it happens with a differential form of Maxwell's equation time domain. So this one FEM technique is okay for a sensor, those who are working 2.45 gigahertz for like with less penetration or without any boundary things and all. If you are working with, it's fine. MOM technique is for the circuits, it is fine, but not for the sensor. And FTTD is for, it's okay for like it is very good technique, but the frequency domain measurements, when you are looking with some of the time domain reflectometer measurements, at that time it will fail. And when you are looking with the BM technique is very good, but it's work with the linear partial difference equation in time domain. So boundary elements, these are okay when you can decide about the enclosures, and then you can see the sensor performance. This it will very much useful when you are testing the prototype. So these are many, not only this, there are many 3D simulation techniques are there. You have to use an appropriate thing and you have to analyze that. So most of the time, like for the sensor design, I will show you require EDA tools if you are looking for the system. It's not about just getting one i7 processor laptop or with this thing. We have to stick with for any of the EDA tools. We have to use number of nodes and cores are important for this thing. So and we use always remote desktops here, but distributed desktops makes very faster. So if someone want to work with EDA tools and all, I recommend they have to go with the workstation laptops than any other models. It's not about the configuration, it's about the how it creates. See, netlist and multiple data it will create. So your processor should have more number of nodes. I have recently I have switched my system for i9 system recently, and with a distributed node. So that makes like my simulations will go in lesser than 15 or 20 minutes. So that's how I like if they are computing, and also they have to use and very good real-time tools for the simulations. And I like to give some comparison of I like to just skip few things like the I like to show directly few tools like uh, some logical concepts when you're preparing. Most of the designers, they start tuning and optimizing and yield, but for me, like we have to be from the basic concept, we have to properly have to choose, and what are the circuit related parameters is affecting for the measurement has to be identified, and tuning has to be made very slowly, and yield goals has to be taken properly. It's not most of the engineers make directly, they put on optimizations and all. They put more things on the machines, but it will not work actually. So of course, at the end of the day, it's only the machine, but we have humans, we have to do come up with more valuable things actually. So we have to design our topology in very valuable manner. So then our sensor will work in a proper way. So uh, just I will skip. Like I like to talk about few softwares. Like this is a ADS. ADS simulator is one of from the Agilent company. It's having both like layout and schematic things. And the best part about this tool is the thermal integrity is there, and we can have we can make this is good for the circuit related things. That means component level design is very good for ADS and AWR tool, and so AWR tool is having those who are working with the 5G technology, and that's very good. Like we can is having good PDKs or the process development kit for the MMIC, and RF PCB circuit design for this thing, and several tools are there like VSS for like system level, and we have got a radar library in that, and analyst is for 3D sensor design, and Axiom for proper 3D simulations, and for antenna synthesis and optimization there is a separate tools. So this AWS simulators is having a separate tools for every this it is a like what is the base for application specific, they have got a different tools for simulation. And ANSYS is the HFSS, like most of the users or the from in India, many people use this too. So it don't have any electrical size and other limitations actually. So it can simulate in a very broad manner. So it's used by many people. So we use HFSS tool for the designing a sensor. So it's very good 3D simulators are available for this. For a sensor designer, just for the sensor designer preparing and very good EM structure simulation, HFS and CST, these are very good tools for start with those kind of work. So and another tools called a CST, this is also very good tools, and is having a we can have an active elements, and also we can have in this tool we can have time domain measurements are very good, and we do have a lot of options apart from the HFSS. We do have like for the sensor design, what I like to say is like we do have some of the inbuilt human tissues models, like starting from skull to every human body parts. Like we do have a specialized models. We can use ready-made models, and above that you can prepare few drawing layers, and you can assign electrical characteristics to those models, and you can come up with the sensors. So basic models are like more than HFSS, and CST provides more human tissue models. And I like to give few features like every softwares are there in the market, and they have their own way, what is that own features, specialized features. There is no I don't like to compare any of the tool. All tools are good in their own way, but I like to just say about some of the features. Say about HFSS work with FEM technique. I said like in a 3D simulations, we have to see those things, whether those models are suitable for your sensor design or not. And CST is a finite integration technique. And most of the time people say HFSS is more accurate. It's like, it's, of course, it's their review. But for me, like both are same. And this CST is a quite faster. It works with the time domain. And HFS having only passive circuit simulations, but CST is having both passive and active circuit. That means a sensor, if you want to prepare any of the sensor like active antenna related things, if you want to make, CST can make it. And HFSS makes mesh and EM analysis in a fast and accurate manner. And CST makes multi-coil, and sometimes if you are preparing any of the sensors with say about split ring resonator and kind of a thing, CST provides some good results for us. Their simulations will be good. Like HFS is only for the frequency domain, and CST makes both time domain and frequency, both it can make. And HFS requires more RAM, and especially commercially tools require 64 GB RAM. And CST is like RAM requires more. If the processor is good, then it's fine. And similarly for like component level design, this is for sensor level or like for EM structure simulation, and this is for component level. ADS, what we are using from ADS element, we do have a lot of equipments from them, and we do have a huge market. And signal integrity and power integrity, and they have got X parameter simulation. That is the one of the best thing only in that tool it is having. And also our measurement is on both electrothermal analysis. Say about sometimes we have to consider temperature variant in that, so ADS provides with that. And we do have like it's having encrypted HPIs and statistical design, and lot of advanced module controls and cadence libraries integrated. But AWR, it is like a cadence itself is providing that tool. It's fast growing, user friendly. You get lifetime license, and just having libraries with respect to MMIC and LTCC. There's a greater advantage working with modern technology of wireless communication, 5G, things under 60 and all this for them is very much easy. And they have got several tools like our MicroOffice, VFS, and lot of this, and various tools. And they give unified models, and many international associations works with them. It will come with a different German, Chinese, Japanese version, and it's having a lot of library. Like what you say that I filter images, like those who don't have much basic concept of microwaves, they can still use these tools for them. Like it's kind of a guide. So they will provide a good library. It will become for design easy for the designers to come up with the. And in short, like I could say about the tools, like if you're working on active devices and if you want to use norm technique or X models and all, you can choose AWR or ADS, both are same. And if you are a sensor designer and you want to come up with a very good EM structure simulation, HFS and CST. So if you want to use FEM technique, you can use that. And if you want to use and fully 3D things, say where TTD models, then you have to go with the CST. But for CST, you should have a very good CPU. Or every simulations, it will take like a couple of hours to simulate. And FICO is just for like if your transmission line only wire and radar cross section kind of a thing, you can use that. And Lumerica one tool, they use like FTTD. If your measurements is with respect to optical, electrical, and thermal effects, you can use the Lumerica. And IA3D is only for the planar structure. It's like cross-sectional solvers. Just for planar things, no filters, if you want, we can use that. And COMSOL is I use the COMSOL also for checking with acoustics inside the Anakin chamber. So few models for that. I'm not a very good COMSOL user, but few things I have. For few simulations, I use that. So according to me, like you can use for 2D design, not with exactly 3D simulations for especially electrical characteristic. You can use if you are work is related with structural, acoustic, fluid, heat, and chemical disciplinary news also. And there are a few simple tools like LabVIEW, MATLAB, front end. This for simple numerical computation, scientific computation, and simple interfaces. I use LabVIEW and GNA Companion for interfacing the software-defined radio for checking the performance in channel characterization. I do communication channel characterization inside the human. So for that, like fat ABC communication and other things, on-body and off-body channel characterization. For that, I will use LabVIEW and also GNO Radio Companion. This is like open source GNO Companion for software-defined radios. I use USRP devices for characterizing these channels. So these are some of my older design which I have prepared, and this is our team. We have got a fusion of many professors and researchers and PhD students and overseas master thesis students. So thank you. Like I think I have taken much time. So it's time for us to discuss.
Thank you so much, sir.
You're welcome.
Thank you for delivering a detailed session on microwave sensors and giving overview of various 3D modeling tools. Participants, you can ask any questions. There is one question on dielectric profiling.
Yes, like it is in chat box.
Yes, it is in chat box. Can the dielectric profiling be used to characterize polymer layers? For example, PDMS layers.
Yes. What happens is like PDMS is silicone things. What happens is like we use different curing agent for the PDMS. So most of the time it will be like just it is shifting our resonance frequency towards certain range. Actually, if we are like in 2.45 gigahertz, if you come with a sensor, PDMS layer, once addition of that, it will shift a little bit. So dielectric profiling characterization, yes, we have got many PDMS models actually. Sorry if I can show a few things. Based on the curing agent and based on the ratio which you are using, say about I will use a 10:1 ratio, some of the silicones. So based on that, their dielectric properties varies. So generally we use PDMS as a biocompatible thing. We encapsulate our sensor with the PDMS so that it will not damage the human tissue. For that only we use. And the characterization, we have got high performance probe, and we have got slim probe which we are having. Based on that, we will characterize. For the frequency from 500 megahertz to 26 gigahertz, we will make it, and we will save those data. Generally, like PDMS which we use here, it varies actually based on the curing agent. It varies from at the 500 at the 2.45 gigahertz. It varies from dielectric constant from 30 to 42. So these are some variations we get it. And also thickness matters for the dielectric characterization. If 1 mm thickness of a thickness of the PDMS layer is different from 2 mm, and how we will grow on that. And also we will prepare a specialized molds for PDMS encapsulation. That also matters. And also there is a very important thing is that what kind of an vacuum things you are prepared to remove the air bubbles in the PDMS. Say about there will be some micro air gaps also, that also contributes, even though it's not visible for us, no air bubbles, but very smaller what is that, like air gaps will be there. And that will make and also pure, and also it varies about like if it is Kapton related, if we are using a substrate, electronic substrate or Kapton, and we are encapsulated with the PDMS, so it will absorb, sometimes it will absorb the humid. So based on humid, the dietary permittivity will increase. So there are many challenges. So we use generally and from the Roger flexible material for the sensors, few sensors, especially with the skin related, and will encapsulate. Hope like Sriram, have you convinced?
Yeah, thanks Pramod for the answer. I was also curious. Dielectric profiling seems to be very interesting way to characterize things. How about AFM-based methods like tip-enhanced Raman spectroscopy and electrochemical?
Can you come again? Oh, can you come again? Right.
Yeah. Sorry, I will. Yeah, I'll be a little slower. So I'm considering why not think about AFM-based techniques, atomic force microscopy, in terms of tip-enhanced Raman spectroscopy and electrochemical tip. Yeah.
Yes, yes, I'm not much aware of those techniques, but what we do is that like for any of our application, currently what is the existing method we'll see, we will interact with the doctors, and we will first learn actually initially first phases like what kind of the sensors has to prepare. In our lab especially, our group is called as a microwave in medical engineering group. So most of our work and what are the resources available here and what we are can do is more with the micro sensing thing. For that we prepare, and also we are stick with the frequency also. So bigger size sensor only we are making. We are not making not with any electromechanical sensor or biosensors. We are making only microwave sensors. So according to that, like yes, I in the talk I showed the microwave imaging that we have introduced. I said like one of the permittivity imaging. Those kind of a thing we have tried. We have not tried with a vast range of frequency, because like when we increase the frequency, the design techniques will be like very difficult. So in one of our PhD student, he was working for not for the medical application, for other application. He used to work on millimeter, like after 50 gigahertz. So it is like once we increase the frequency and all the challenges with respect to designing and other things varies. And also when we have to come up with a sensor, we have to keep in mind that what kind of a power we are introducing, and also what is the frequency. If you are using very high frequency, it will penetrating depth will be more. Say about I want to see what is the changes or what is the disorder at the bone level or fat level, or say about for the sarcopenia patient for the muscle layer. So we require more radiation to be in that region. Say about if you are increasing the frequency, there we will because ISM band is for the medical this thing. So those frequency are like very promising for us to be in that layers. So that's why we have not made any experiment above like 6 gigahertz. We have designs antennas for the communication and other things. We have come up with devices for air frequency, but sensor we have not made anything. We have made only few sensors, which works with 2.45 gigahertz and 5.8 gigahertz. So sorry, Sridham, I am not aware of other things.
It's fine. I was just curious if you had tried, but I understand the focus of your lab. So yes.
Yes, you say as a researcher, you also know that like once we start with that, our challenges, we have to see what is the resource available. Yes. And we have not tried. And also for this applications, what we have prepared for that, we have to like, and also we have to look for an ethical approach also when we are looking for clinical trial. So that is one regulatory act we have to follow. That's many issues that you are also must be aware, I guess. So and also bringing some devices to the lab. That's required.
Thanks a lot, Pramod, for the answer.
Yes, definitely we'll have a good conversation. I like to interact with you even after this session, because
Sure, we can catch up.
sorry, I did not attend your presentation, but like
That's fine.
I'll collect your contact details from Venkatesh, and we'll definitely have
Sure.
a good interaction after this presentation.
Participants, any more questions? You can unmute yourself and you can interact with the speaker. So we are happy to note that. So Dr. Pramod sir, he was one of our formal faculty in our EC department, and one of our alumni, he was in electrical department. He is also one of the researcher in his own lab. Am I right, Dr. Pramod sir?
Yes. His name is Arvind Sell. Yes, he attended actually. Just he got some work in the lab. He just he left.
Yes. Any more questions, participants?
If someone is hesitated, they can ask in the questions even in Kannada or in any language. If they're like that is also fine.
Yes, if no more questions, we'll conclude the session. So, Varshini?
Hi, yes, sir. I thank Dr. Pramodar, Division of Solid State Electronics, Department of Electrical Engineering, Uppsala University, Sweden, for enlightening us on the design of microwave sensors for biomedical applications. From the webinar, we were enlightened about the dielectric profiling and the color profiling. We were given an insight on microwave bone mineral density, the microwave sensors, and the microwave phantom development. A detailed explanation was given about the development of sensors. We were made aware of the cylindrical and rectangular phantom models. We were given a detailed explanation on the design of microwave sensors for the biomedical application. We were made knowledgeable about how to achieve the concept approval. We were also told about the classification of models and the different classes of EM simulators. We were told in brief about the FDM, MOM, the FTTD, and the BEM. We were also given an insight of the EDA tools that can be used for simulation purpose. We were enlightened with some logical concepts like tuning, optimization, and yield. We were given information about the CST Studio, which could be used for sensor design. We also learned about the HFSS, ADS, and the AWR simulators. The features of various other simulators that could be used were also explained. I thank you once again for your valuable time and for providing us lots of interesting facts and information, sir. Thank you, sir.
You're welcome. Thank you.
Thank you, Varshini. Participants, we have sent the feedback link through registered email. So you can respond to that feedback form within 2 p.m. And you will receive the participation certificates only if you answer more than 50% of the questions with right answers. So spend your time on answering, okay, and submit within 2 p.m. So I thank all the participants for joining.